All right, so welcome everybody. My name is Andrea Malchiodi and I'm the current director of the Georgi Center. So the meeting, Optimal Transportation Applications, has a long tradition here in Pisa. First edition was in 2000, and now we are at the 11th edition. So any progress since? No, I'll just say a few words about the center, and I promise I won't take much of your time. So the center was started its activities in about 2000, formally as a research laboratory of Scuola Normale Superiore, but with the goal of being an aggregation point for the whole mathematical community in Pisa. Of course, there's a big community from the University of Pisa and also a small group from Scuola Superiore Sant'Anna. So these two institutions, especially the former, contribute crucially to the activities of the center, also with the help of Fondazione Sansone. So the main activities since the start of the center have been workshops, schools, and research in pairs, and we also started recently a colloquium series. We have visiting positions of two types, for short term to run research in pairs or groups, and we have typically 2 years postdoctoral positions with the opening typically in November and December. It should come out soon for this year. Basically, that's all I wanted to say. So I would like to thank, of course, the organizers for bringing up this very high-quality event, and also the staff of the center for their constant and valuable support. Thank you.
So thank you, everybody. Welcome to this meeting. This is a tradition which started almost 25 years ago, and it is amazing for one like me, who was here from the very beginning, to see how this subject has ramified, the community has grown in these years, and I think now we are all aware that it is almost impossible to fit this subject into a single book. Someone tried a few years ago, and also a single meeting, but with the other organizers, we did our best to represent all the communities working of optimal transport. So I hope you will enjoy the meeting. Today I will be the chair of this morning session, and also let me take the occasion to thank the staff of the Centro de Giorgi, which is more and more professional, helpful, and then as time goes on. So thank you very much. And let's start immediately with the Professor Theo Stum from Bonn University. He will talk about Wasserstein diffusion on multidimensional spaces. Thank you.
Yeah, thank you. It's my great pleasure to be here. And of course, also from my side, thanks to the organizers and for not only organizing this meeting, but this excellent series of meetings, which really pushed forward this field since 25 years. I will talk on a topic which is also quite constant topic. So this is in principle something which I started with Max von Renesse 15 years ago. And at that time, we could solve this problem on spaces on dimension 1, so intervals and S1. And now I want to present you some progress on this multidimensional setting. And I hope that at least some building blocks of this result are of independent interest for many of you. Oh, what's that? Okay, let's start once again. The topic is Wasserstein diffusion multidimensional spaces to fix the setting once for all. For M, here is always a closed remaining manifold, so compact without boundary. M is the normalized volume measure. If you like, you could also, at most places, think of Euclidean space in Gaussian measure. But okay, let's think of this compact setting. And the aim is to construct not only a first-order calculus on the Wasserstein space, but a second-order calculus. So this means we want to define a natural measure on this Wasserstein space, which, in addition to the distance, then will give us a Dirichlet form and a diffusion, which we call Wasserstein diffusion. And the The measure which we have in mind should be characterized, at least heuristically, in this way. We think of a kind of uniform distribution on whatever all measures, and put in here the entropy as a rate function. Why? Because we have in mind, if we switch off a noise, then it should be the gradient flow of entropy, which is the heat equation. So our stochastic process should be a stochastic perturbation of the heat equation. And by fundamental work of Otto and many others here in the audience, we know heat equation and entropy is closely related. So gradient flow of entropy is one of the key objects in this theory. Why not considering a randomly perturbed gradient flow of entropy? So if we have this measure more or less for free, we get this Dirichlet form, or pre-Dirichlet form, let's say. I write it a little bit imprecise without lim-inf and all these things. But we have all data, we have a measure, we have a norm of a gradient. This is the Otto gradient. So we have a Dirichlet form. Up to the question whether it's really a Dirichlet form, whether it's quadratic, closable, and so on. But we know what we are looking for, let's say. Then we have to prove that it really works. Let's come to this. Here, P star is non-existing. Therefore, I can tell you a lot of stories, but it does not exist. The idea is it's a uniform distribution on the space of probability measures. And I give you a little bit more heuristic than why this is a good intuitive meaning. So this is what we call entropic measure. We started with all these things in the paper with Max von Renesse. At that time, the underlying M, the manifold, was one-dimensional. We could only do it for one-dimensional spaces. Okay, experts in optimal transport are not that surprised. In one-dimensional optimal transport is absolutely explicit, and it coincides with many other transformations, of course. Yeah, it's sometimes not really clear whether it's an optimal transport argument or an argument coming from a completely different field. Okay, so this is the measure which we first have to define. Actually, I should say there are two challenges. Construction of this measure. The second challenge, actually I could do this already some years ago. Second challenge is really give a meaning to this pre-Dirichlet form and prove that it's not zero. This is really a big challenge. So this famous group, Savary is missing, told us that on every metric measure space we have always a Dirichlet form, but they did not tell us that mostly this is zero and how to exclude that it's zero. Okay. To construct this measure, which is the first challenge, okay, we have this uniform distribution, which is not existing and so forth. Now there is a trick. We do not do this on the level of measures. We do not write down formulas in terms of measures, but in terms of conjugate measures. And my interpretation is this is something like Fourier transform. If you get stuck in this picture, you go to another picture. And in the other picture, you can do it better. And we do not have explicit formulas in this picture with measures. We have explicit formulas in the picture with conjugate measures. What are conjugate measures? Okay, you all know the C conjugate. And in my case, the cost function is always distance square half. So this is the standard setting in all this is in this geometric context. The C conjugate is what you know. This is the generalized Legendre transform. We say that a function is C-convex if its double conjugate is the function itself. And with curly K, we denote the C-convex functions. So concerning regularity, these functions are as good as convex functions. Yeah? Or these are just convex minus a distance square function, essentially. And yeah, since we have Jan Prenet here with us, you know whom to ask. Concerning this result, we know that each probability measure is uniquely characterized by a C-convex function, modulo constant. So for every probability measure for X is a unique C-convex function, modulo constant, such that this measure is the push forward of the exponential function of this gradient with respect to the uniform distribution on this manifold. So we have a one-to-one correspondence between probability measures and C-convex functions, modulo constants. And we know how to invert, roughly speaking, these transport maps. Yeah? So this is the transport map for gradient of phi, and we want to invert this transport map. Inverting transport map is not really the technically correct way, but we have a C-conjugate. And we know that every C-convex function is a conjugate. And of course, by definition, the conjugate of a conjugate is the function itself. And kind of new ingredient is that this conjugation map is continuous with respect to the H1 norm. This is crucial because then all other maps are also continuous. And what we do is we extend this conjugation now to the level of measures. We know there is a one-to-one correspondence between measures and convex functions. Convex functions have conjugate. Conjugate have, again, measures, and these are the conjugate measures. And since this is continuous in the corresponding topology, this is a continuous map on the level of probability measures. So we can switch between measures and the conjugate measures. One is as good as the other one. And as I mentioned, I would regard this a little bit as Fourier transform. It has similar properties. Dirac goes to smooth or to flat cases go to Diracs and so forth. We will see this in a picture here. So if you have mass which is located on this sets, let's say if there's a uniform distribution here in this region which is mapped to a Dirac, then the conjugation map in principle tries to invert this transport map, which is possible if you have smooth transport maps. Then conjugation means just reverting the transport map. The challenge, however, in particular in this approach, which I have, where I end up with, is that we have a lot of measures which are concentrated on Diracs. So if I have a uniform distribution and I map it to a countable number of Diracs, my transport map looks like that. If I want to invert that, okay, I have to map this Dirac to this set. What does this mean? The conjugation map tells me exactly what it means. I can conjugate the C-convex function, and then I get a transport map, and it turns out that this Dirac is mapped to the boundary of this set. Not uniform distribution, this is what I do not know, but I know that it is not going into the interior. It moves always the mass outside of its islands. And okay, in dimension 1, this is very easy because in dimension 1, all this picture, this is what we did 15 years ago. The picture is very easy. You have probability measures here on the interval. They correspond to increasing functions. Conjugation map just means you revert that. You exchange x and y axis. Increasing function for inverse is also increasing function. Up to this ugly question whether it's the left or right endpoint, which you have to choose. And then the increasing function again corresponds to a probability measure. So in dimension 1, it's just the increasing function, which is mapped here. And this is now the multidimensional picture. This is exactly what we did in dimension 1. In dimension 1, there was not this need of using convex function. So now there is even more optimal transport picture behind that. Okay, perhaps I first draw your attention to this last result. This is the reason why I'm interested in the conjugation map. Because the entropy of a conjugate measure with respect to the uniform distribution is the entropy of a uniform measure with respect to the given measure. So, and in our heuristic definition of an entropic measure, this guy pops up, which is a little bit unnatural. So we use the conjugation map and so on, and then we end up with a traditional entropy. So we need this relation. And of course, there might be other transformations between measures which allow for this formula.
Second slide, there was entropy mu with respect to n.
Yeah.
So why now you're telling me?
Okay, actually, maybe better put the C here. Erase it here and put it there. But since it's involutive map, you can put as many C's as you want if you do it the same on both sides. But you're right, for pedagogical reason, it would be better to put it on the right-hand side. Yeah. But this is the key relation. Okay, and this is the reason why we are interested in this conjugation map. And now there is a challenge, and maybe some of gifted young people are motivated to improve the current result on that. If you think of this picture here, I told you if you have such a situation, you map uniform density to a Dirac, and then the inverse map leaves this without mass. I can prove this only for the sphere and for the torus. So everybody is invited to prove this for every smooth manifold. I guess that it's true, but it was too hard. I asked several people. Most of them did not reply. I guess they also had no proof, therefore. And those who replied also did not know the answer. So the question is, if you have a Dirac and something else, and you map this measure to the uniform distribution, or the uniform distribution to this measure, and then you make a kind of inverse map. This inverse map leaves the interior of this set without mass. The question is it really an open set? Yeah? Of course, you immediately have that there's a measurable set of size lambda, which is the pre-image of this Dirac. But is it without, does the boundary have no mass? So can you pass to the interior or to the closure, if you like? So is this set really open? Measurable is for free. And if we know this open set has no mass, then of course the consequences are obvious. If the measure mu is discrete, so it consists of Diracs, then these pre-images are a lot of open sets which have no mass. So the mass has to sit on the complement of all these open sets, where the open sets have already the total mass. So it cannot have an absolutely continuous part. And on the other hand, if mu has full topological support, then the conjugate measure can have no atoms, because atoms squeeze open sets. They move away the mass from given open sets. And this is the, in some sense, optimal transport geometric background. So for most of the remaining results, I assume that we are on the torus or on the sphere. For my personal aims, this is okay, because until now we had been limited to dimension 1. So the big push forward, of course, is to get rid of a dimensional restriction. But of course, this is a little bit frustrating that you need this high degree of symmetry, which probably is not needed. And now coming to this original question of Robert, what should be this, the meaning of this formula? What is the P star and so on? And to introduce to that, I start a little bit more general. I start with an introduction to the Wiener measure, going back to, as far as I know, Feynman. So this is a heuristic interpretation of a Wiener measure on the real line, on the interval 0, 1, let's say. And the idea is that the Wiener measure is defined as follows. You have a uniform distribution on continuous functions, again, non-existing, and you weight it with the energy of the paths. Okay, experts know the energy is infinite for each Brownian path. You can ask what is this good for? But indeed, this is very helpful, because you will see at the end of this slide that this gives you the precise definition of Wiener measure. How to do? Instead of looking for the energy, you give yourself a finite dimensional partition, and you replace the energy by the minimal energy if you fix a continuous function on this given time instances. Yeah, you have T0, T1, T2, and so on. And at this point, you evaluate your continuous function. And in between, you replace this function, which you do not know anyway, by the function which has minimal energy. which is the piecewise linear. Yeah, you draw a piecewise linear trajectory such that it matches with given values. The energy of this piecewise linear function is exactly this expression. And of course, you probably know that if you exponentiate this expression, you're almost done with a Wiener measure. So in this formula, you then have only to say what is the distribution at this given points. Okay, here again, the uniform distribution enters the picture, but now a uniform distribution on a n-fold copy of Euclidean space, you know. You have a guess. This could be Lebesgue measure. It's a good candidate for uniform distribution. So if you replace this measure by a Lebesgue measure on n-dimensional space, you have a right formula. So because then this is a consistent family, or projective family of probability measures. So Kolmogorov tells you there is a unique limit, and you are done. So this way, from this heuristic formula, with the energy replaced by the energy of a piecewise linear function, or the energies of its minimizers given the constraints, and the uniform distribution on these given points replaced by Lebesgue measure, you finally obtained the correct formula. And this way, of course, you also have an interpretation what this should be. In some sense, this is the infinite dimensional Lebesgue measure, okay, which does not really exist, but with this scaling factor together, it makes sense. You can scale both together. Okay, now why doing this large preludium? Because we do the same now with the entropy in the place of the energy. And a little bit different setting, of course. We are not now on an interval. We have a multidimensional space, and we are not looking for measures on functions. We are looking for measures on probability measures. Probability measures on probability measures, they are characterized by the distribution of these vectors, random vectors, if you give a partition of your space. Yeah? You have your space, you divide it into cells, n cells, and then you ask what is the vector with a volume of this, and that cell. Given this partition, you have plenty of possibilities to create such a partition. For each partition, you obtain a random vector, and you hopefully can write down the distribution of this random vector. If you can write down this, you are done. And this is this result here. Yeah? If you can write down this random vector, and if this is consistent in the sense, if you pass from a partition to a finite partition, the formula should be consistent. You integrate out the additional degrees of freedom, and you obtain the previous distribution. But we don't have a formula for the finite dimensional distributions of this guy. This is just a matter of fact. This is also a matter of fact in dimension 1. But we have a formula if we would reverse the order of these measures in the entropy. This is just a matter of calculation. For this entropy, we have a consistent way to write down the contribution of entropies if we pass to partitions and finite subpartitions. So this is in some sense what can be done. And now we construct this, again, trying to choose here a uniform distribution, whatever this is. This can be resolved. Then we have a measure Q, and to this measure, we apply the conjugation map to pass to the measure which we are looking for in our original intention. Therefore, coming to this question, the new conjugate in some sense depends a little bit on which level you are. At the moment, we are looking now on a different distribution. We look for a distribution on probability measure, which has this reversed entropy as a rate function. Because we know, or I know, that for this, things are more successful. And this is the reason which I just explained to you right now. So we are looking now for this measure Q, and we look on the entropy. So what do we have to think of now? We think of a partition into n cells, and we want to replace the entropy, which we do not know, by the entropy of a measure which have a given marginal, the minimal entropy of all probability measure with a given marginal. And given marginal means measure within one cell. And if I know I have a probability measure which has this mass in this cell, mi, then this is the minimal entropy. Also for this conjugate entropy, for this reverse entropy. Also for this reverse entropy, the minimal entropy is obtained by those measures which have constant density in each given cell. And constant density within each cell can be calculated explicitly. This is just the logarithm of its density times the volume. And so you have an explicit formula for that, and this formula is consistent. So if you pass to a finer partition, this formula is just meaning that you integrate out the variables.
Yeah,
no.
Yeah,
but it's not consistent. This is already in this one-dimension case. Yeah, if you make in the one-dimension case, what we observed is if we make partition on the x-axis, we are lost. If we make partition on the y-axis, we can write down things. And this partition in the y-axis, this is now the conjugate measure. And if you do that, then there's another challenge. You have to argue what is a uniform distribution on probability measures. Now it's more complicated because for functions, you can say this is an infinite product of a real line. For probability measures, even in this one-dimension case, it's not the product of a real line. It's really the simplex. And now an appropriate measure on the simplex is this measure. You see again, like for the Lebesgue measure, it's not normalizable. It's an infinite measure. It can be normalized only if you combine it with a rate function. Now, the combination of this and this rate gives you something which produces a limit. Yeah, Peter positive. Peter 0 would be this guy. Peter negative, okay, even worse. And yeah, and the other nice thing is when we obtain this result, this is a probability measure which is well known in statistics. This is the so-called Dirichlet-Ferguson measure. The explicit formula is here. If you give yourself a distribution of measures, you have the simplex in some sense. So this with this Dirac means you are integrating with a simplex. You have a density x. Without the beta, it's 1 over x, which is not integrable. With a beta, it's integrable. And this is just the density which makes it to a probability measure. This is the formula which comes out of our calculation. Fortunately, people in statistics, they already found an equivalent characterization, which is much more intuitive. Namely, it says the distribution under this Dirichlet-Ferguson process can be described very easily. So it's almost every probability measure is a discrete measure, consists of countable many Diracs. The locations are uniformly distributed in space. You just throw countable many particles in the space. And then you have to only ask what is the mass of his pieces. And for this, you have a stick breaking process, which means there is only one parameter, which is this beta. And this says you have a stick of length 1, you break away one piece, depending on beta. This is the beta distribution. This is the mass of the first particle. When the rest is rescaled, you break away a piece, this is the mass of a second. The rest is rescaled, you break away a stick, this is the mass of a first particle. And so you have particles which have the weights of which is decaying exponentially. The largest one is roughly of order 1 over beta, the mass, and then it scales down exponentially. And you have this explicit description, uniformly distributed particles with masses independently of a location given by the stick breaking process. And this is now our Dirichlet-Ferguson process. And okay, this is why I made this complicated description of a conjugation map. We are ending now with a discrete measure. And we have in mind that we have a transport map from Lebesgue to discrete, and we want to invert this transport map. This is intuitively what we do. And inverting this transport map means we produce a lot of holes in our space. The volume of the holes is 1, and the mass is sitting on the boundaries of these holes. yeah, this is the picture here. We have this holes, which or the mass, which, so here's a typical measure produced by the Dirichlet Ferguson. We have this transport map F, we revert the F, and now we transport Lebesgue measure to the Dirac is transported to this, but we transport Lebesgue measure, and Lebesgue measure is then sitting on the complement of these islands. And the size of the islands is 100%. So there is not much size available for the Dirichlet Ferguson process. Here are some pictures for beta. I don't remember, I think this was 15 and 30 and 50 or something like that. So what you see here is these white regions are regions without mass, and the mass is sitting somewhere on these black boundaries. I do not claim that it's uniformly distributed. I only say there is no mass in the white regions. Yeah, of course, in these cross points, this is then a kind of fractal-like structure. These very tiny things they are squeezed into these corners. We have some basic result, at least if we are in this setting, sphere or torus, that a typical measure under our entropic measure has no atoms and no density. This is, of course, a nice probability measure. Yeah? It creates all these guys where non-mathematicians are lost. It is also not so surprising, because if what you should have in mind is this picture from the Brownian motion. Brownian motion, we started with saying we want to have a probability measure on continuous functions, which in some sense regard for energy as a rate function. At the end, we ended up not with C1 functions, as would be nice for energy. We end up with C1 half. Yeah? Brownian paths are roughly C1 half. It's between C1 and really bad. And now we use the entropy. The entropy, roughly speaking, says we would like to have a density. This is more or less saying what means finite entropy. Of course, we cannot expect that in the limit. This is a typical phenomenon in infinite dimensional analysis. If we pass to the limit, we do not really have this control which we started with. We do not have measures which have densities, but it's not really bad. It's not atoms. No atom is allowed because we have an entropy which controls that. If we switch off the entropy, the beta to zero means we switch off more and more the regularizing effect of the entropy, then we get Diracs. So the Diracs are essentially uniformly distributed. If we increase the entropy more and more, then we approach the uniform distribution. It's a Dirac on the uniform distribution. Switching off means a uniform distribution on Diracs. Increasing the regularization means just the opposite. So this is, in some sense, consistent with what we expect. Oh, where's the large deviation result? Oh, maybe I have really not the very last version here. Sorry. Actually, there is a beautiful additional result, which unfortunately seems not to be on this slide. Okay, Jan already complained that there is written UCLA 2024. It's this year, but maybe a little bit too early. In the meantime, there is another result, namely there is a large deviation result. If you look on the large deviation of this measure, then the rate function is really the entropy. So this we did not know 15 years ago, even in dimension 1, despite the fact that at that time, actually, we could have found this in the literature. In multi-dimension case, it was not existing in the literature. It was very close to a result for the Dirichlet Ferguson. but also for Dirichlet-Fulkerson large deviation was not proven so far in the precise way. And this is another justification that all this heuristic really is a very solid way to approach that. So I would recommend have a look in the paper on arXiv. There's the large deviation result in it. Sorry for missing that. Now we come to the kind of second part, namely to come to the energy. So we have now the entropic measure. We have a natural, let's say, measure. It's not really a lab-back measure. It's more, and it's not a Brown motion what we construct. It's more like an Ornstein-Uhlenbeck process what we construct on this Wasserstein space. And now we want to define this Dirichlet form. And to start with, we define cylinder functions. Many of you know quite well what this is. So we define functions on the space of probability measures in the following way. We have these functions v1 up to vk. These are like coordinates, and this v1 up to vk are integrated with respect to mu, and then functions of these coordinates are capital F. These are C1 functions. And then for the cylinder functions, I can calculate the norm of a autogradient. This is just, the square of it is just this bilinear form in capital F, evaluated at this point and with this pairing of vector fields. So for most simplified object is you forget the capital F and you have just one function v, and then this is grad v squared d mu. So this is the basic function on this space. You have a function, integrate each measure against this function, integral v d mu, and then the gradient square is integral grad v squared d mu. And this is what we should have in mind. Then we can define a pre-Dirichlet form, and this is still nice. Here, the advantage if we start with cylinder functions and not with Lipschitz functions is that we immediately know that it's bilinear. So on this level, infinitesimal Hilbertian is for free in some sense. And fortunately, there is a result from last year from Giuseppe Savary, Sordini, and three people, hopefully okay. Which says this is equivalent to also the approach where you start with Lipschitz functions, which, by the way, then also gives the fact that the approach with Lipschitz functions is infinitesimal Hilbertian on this space. Okay, now from this pre-Dirichlet form, we pass to the Dirichlet form by relaxation. This is, in some sense, the standard way. And without any additional effort, we see that this is strongly local, regular Dirichlet form, and it coincides with a Giga energy. This is what I already mentioned. And therefore, as a consequence, there exists a strong Markov process with continuous paths, and this is what we would call Wasserstein diffusion. What remains open is whether this pre-Dirichlet form and the Dirichlet form coincides on the pre-domain or on any class of functions which you know explicitly. Is there any class of functions where we know this guy explicitly? So if this is given explicitly, in particular with the cylinder function, you can write down explicitly the formula. And this question in the language of classical Dirichlet form theory means the closability question of a pre-Dirichlet form. And in dimension one, Max von Renesse and myself could give an affirmative answer to that by the integration by parts formula for the entropic measure in dimension one. But this seems to be out of reach in higher dimension. So what is behind that is that in dimension one, we could prove explicitly how the entropic measure changes if we push forward all measures by a standard transformation of a space, which is a push forward by a smooth vector field. And we have an explicit formula in probability. This is a Giordano theorem. This is the way how Brownian motion or Wiener measure changes if we push forward everything by a smooth transformation. This in higher dimension, I tried, several other people tried, so I think this is out of reach. And therefore, for quite a while, I stopped. So until this part, I was already several years ago. But I did not want to publish a paper where maybe 2 years later, someone proves that everything refers to the zero energy. And so I got stuck, and I wanted to prove that at least this energy is different from zero. And I was confronted with this question because there are also other approaches where you end up in metric measure space theorem with an abstract construction. You could pass to the Giga energy, but you do not know whether it's different from zero. And here, so, or another way, whether the process moves at all. Does it move, or does it get stuck forever? And I present now a result which is not a complete answer. It's far away from the answer to the closability, but it's really proving that it moves. It does not move. I cannot prove that it moves in each direction. If you think that these basic functions are like coordinates, I cannot prove that it moves in each coordinate, but it moves in plenty of coordinates, let's say. Okay, some information or some technicalities. I think most of you know that. So we have this Giga energy with the lim inf, but fortunately this is also given as an integral of G square, where G is minimal or any weak upper gradient. Unfortunately, it's a weak which is inside there, and this is what we have to deal with. So weak upper gradient can be characterized by this inequality, that we have this inequality for gradients, but now we do not request that this holds for every curve, but for almost every curve. And almost every means this holds P almost every for every P, capital P, which is a probability measure on absolutely continuous curves with bounded compression. And now to prove that what we have to prove is that zero is not a minimal weak upper gradient. Or even better, that a certain epsilon is a minimal weak upper gradient. And to handle that, we choose a specific probability measure there, namely our invariant measure pushed forward by so-called diffeomorphism, Lipschitz family of isometries. I hope I have a description on that, yes. Lipschitz families of isometries. So out of my invariant measure, I construct such a probability measure on paths, which by construction then has bounded compression. So this is my kind of test. And roughly speaking, I just push forward these invariant measures along in such a way that at each time it's the same. This is even better than bounded compression. And Lipschitz family means I have maps on my manifold. Phi naught is the identity. It's an isometry for each t. The time dependence is Lipschitz, and it maps a given point x0 to a given point x1. So I just want to guarantee that I have a family which gives me a transport from x0 to x1 for any pair of points. And if I have a Lipschitz family of isometries, then I can prove a kind of Poincare inequality. This is my Giga energy. This is my F. And okay, I have this L, which is the constant of this Lipschitz isometries. And then I'm already done. I already have a non-ternary result. The reason is that if I look in this inequality, I integrate it with respect to my measure, P. Then with respect to TT, this P essentially is invariant. I have a B beta. And so I finally get the G independent of mu. And squared, then I have G squared dP, which is exactly this quantity. And I have here the square with some shift and so forth. So I get this basic lemma. And with this lemma, I can then prove, well, you see here, I have a F evaluated at mu and at this transported point. So if I have a so-called antisymmetric function, I have twice this value, and I can estimate the energy from below by the L2 norm. So the energy is different from zero for any non-constant non-zero function. okay, non-constant is guaranteed by antisymmetric. And another result here is if I have a Lipschitz function, these are my standard test functions here. This function has non-vanishing Wasserstein energy. More explicitly, I can estimate this by Lipschitz constant squared. This would be, in some sense, 1/2 of this Lipschitz constant squared would be the sharp value. I need an epsilon, and epsilon is maybe very small number, which comes from estimating the probability that my entropic measure puts a mass in an epsilon neighborhood. And this is at least a positive number, and then with this number, I'm done. And with this result, I'm also done. Thanks for your attention, and I'm happy for questions.
Actually, no. Okay. So other questions, comments? Yeah, there is a question from behind, and maybe we can circulate the... Forse è bene se lei lo fa girare.
Just, I have one question. So your construction allows to construct, you have a probability measure over measures, then you can pull back to get the probability measures over convex functions. And I wonder whether you could, because space of convex function is more simple, maybe could it be possible to start directly to construct a probability measure over convex function with rate function, which would be minus the integral of the log of Monge-Ampère or something like that?
Yeah, we thought on that. In dimension 1, we actually had in mind more of this idea to have a probability measure on increasing functions. So in dimension 1, our picture always was increasing function. Instead of Brown motion, which is on arbitrary functions, we had this additional constraint increasing, which is very close to convex. Yeah, it's just one order of differentiation. And with this increasing function, also the picture was very easier because increasing function or inverse of increasing function seems more or less to be the same. Here, I did not see any advantage. And the picture, on the other hand, for me, it's more intuitive to work on the level of probability measures, yes. And compactness and so on, I first of all get from probability measures, and then I transport it to convex functions.
Yeah. Okay, so yeah, thanks for very nice lecture. So I have a question related to the use of the heat kernel in the construction of Wiener measure. So one thing is of course to go in this entropic Wasserstein picture, but the other picture you showed at the beginning, it just comes from iterating the heat kernel and then interpreting that as kind of a path integral. So is there some way in which this construction passes to the limit?
I only know this way, because anyway, you don't have a linear ordering. You really have to think of the cells, which do not just if you leave dimension 1. In dimension 1, it's very similar. This is what Max von der Nesse and myself had in mind here, just mimicking Wiener measure construction. In this higher dimension, I think the appropriate interpretation is that this heat kernel, the discrete heat kernel, shows up as the minimizer of energies for these piecewise linear curves. This is my best interpretation for the moment. And I think this is, yeah, I do not know a better way in this entropic picture.
Thanks. Yeah, a question in line with the first one. I wonder, so it's clear that this last part of your talk is very related to the underlying structure being smooth somehow. But the first one, in particular, the construction of the conjugation map, seems very. Of course, you use this beautiful Brevier-Bekan theorem about existence of maps, etc., etc. But still, I mean, you could
No,
have
but
these C-concave graphs, you flip them.
Yeah,
you push forward.
the continuity of a conjugation map needs the compactness.
Oh, okay, fair enough. That's that.
Yeah, but
Sure.
without the continuity,
No, but I
things
mean,
break down.
compactness is one thing, smoothness
Okay.
is another thing. So
Yeah,
we
yeah.
are
No,
two
no.
different- yeah.
Smoothness is not really crucial.
Okay.
Yeah, yeah.
Thank you.
But you see, for the precise interpretation, then, in order that things are as you would like to.
I understand that.
I even can do several things only for torus and spheres.
I understand.
Even if I think this should be a general Riemannian result.
By the way, what's the conjugation of a delta?
Sorry?
What's the conjugation of a delta? We were wondering.
The conjugation of a delta is a spherical cap. Of a Dirac one.
One. We were wondering, we were not able to.
This is a Dirac at the antipodal point.
Okay.
Yeah, because
Fair
you
enough. You're
move
pushing, yes,
all
pushing
mass
everything.
as
Okay,
far
okay,
away as
okay,
possible.
Okay. Thank you. Great.
Because the corresponding cell is
The
the
whole
world
sphere
without.
except, yeah.
If a Dirac is at the south pole, the mass transported to that is everything besides the north pole.
Thank you.
Okay, so welcome back, and let's continue with our program. It's a pleasure to introduce Fabio Cavalletti from Milano University. He will talk about optimal transport between algebraic hypersurfaces. Grazie.
Thanks a lot. So it's very nice to be here. Thanks a lot to the organizers. Okay, so what I would like to discuss, to tell you about today, it's an optimal transport problem between algebraic hypersurfaces. So the basic question from which we started was, let's say, what is the optimal way if you want to deform a projective hypersurface into another one? Obviously, this question is very vague. I mean, optimal is not really well understood. I mean, anyway, so our starting point was, okay, this was at the beginning of discussions with the colleagues of mine when I was still in CISA. So we somehow try to find a common ground to discuss something. So in the end, we thought that trying to use the point of view of measure theory, so introduce an optimal transport distance between complex objects could turn out to be an interesting project. So the idea would be to, let's say, start from an algebraic hypersurface that then I will introduce and associate to each of these hypersurfaces a probability measure in a most natural way, let's say, and then define an optimal transport distance between two probability measures so introduced. And in the end, see if we can draw some properties or application and if this construction turns out to be of any use. Okay. So this is a joint paper in collaboration with Paolo Antonini and Antonio Lerario. And indeed, we were all of the three of us in CISA. And yeah, so now we are not anymore in CISA, but Antonio actually still in CISA. Yeah. Okay, so the first point is to start from see what these algebraic hypersurfaces we have in mind and how to associate to each of these objects a probability measure. So the starting point is therefore a polynomial. So you start from a polynomial. You fix n and d. D will be the degree. N will be the number of variable. And so our starting object is this homogeneous polynomial that we denote with P and D. And we have just a linear combinations with a coefficient in C, and you have this monomial with a multi-index that sum to the degree. Okay, so this is just very classical homogeneous polynomial of degree D in n plus 1 variables. And the object that we have in mind is it's a zero locus. Okay, so if you take an homogeneous polynomials, it's zero set, so the place where the polynomial is zero. Since the polynomial is homogeneous, it's naturally a subset. Sorry. It's naturally, can I go on the other side? No, just here. No, okay. And okay, so it's zero set is a subset of the projective, complex projective space of n dimension. Okay, this is because obviously since the polynomial is it's homogeneous, if you have a zero, if you multiply that zero times a complex number, still you have a zero for the polynomial. So it's naturally a subset of the projective space. And the good part of considering an homogeneous polynomial is that CPN, it's a very symmetric ambient manifold, it's a compact manifold, and it has a very natural Hermitian structure that is induced by the Fubini-Studi metric. Okay, so what is this Fubini-Studi structure? Okay, you can start from if you see CPN as the quotient of Cn plus 1 by the identification, on Cn plus 1 you put the standard Euclidean metric, then you go on the sphere of S2n plus 1, okay, still with the Euclidean metric, and then you have to do again one quotient that is identify all the orbits via the imaginary multiplication by E. And so what you want to do, you want to say that you can define the Fubini-Studi Hermitian structure to be the one that makes this final quotient to be a Riemannian submersions, okay? So it means that it's just all the orbits on S2n plus 1 are all at constant distance. Anyway, so the object that we have in mind is this complex, it's this zero locus, and from the point of view of the regularity, I mean, this Z of P can be possibly a singular manifold, but anyway, it's compact, it's complex, and has Hausdorff dimension 2n minus 2, okay? And in the case in which this object is this Z of P is not regular, we call the set of polynomials for which Z of P is not regular is the discriminant, okay? Is this here set here, delta ND. And for us, the discriminant is not just that the manifold is singular, but it's the equation that defines the zero locus is singular. It means that the set of a polynomial is in the discriminant if there exists an element that annihilates the polynomial and its gradient, okay? So it might be that the manifold itself is not singular, but the equation that defines the manifold is singular. Okay, so to each polynomial, we associate its zero locus. And now we want to define a measure, a probability measure on the zero locus, okay? Then if the polynomial, as we said, it's not in the discriminant, then Z of P is an oriented, smooth, complex submanifold. And the volume measure is just the one that you can induce by the ambient metric that you have on CPN. So it's just the volume measure induced by this Fubini-Studi structure, okay? So it's the natural one. And the interesting part that actually is more or less, yes. Yeah, actually it's this comment here, thanks. So the interesting part is that then actually, at least from my point of view, started to be very interesting. These things is that if you have a smooth, if the zero locus is smooth, then its volume does not depend on the polynomial. It's just fixed. Just depend on the degree times the volume of CPN minus 1. If you want, you can think about these things as the analogous of what you have in dimension 1, where you know that if you have the number of zeros of a polynomial of degree d is just d. Does not depend on the polynomial. This is just the multidimensional analog of these things. So if you have an homogeneous polynomial, its zero locus has volume that does not depend on the polynomial, just depend on the dimension with this factor times the degree, okay? And this, if you want, says that the normalization factor of the volume does not depend on the polynomial itself. This, if you want, can be seen by computing this volume by taking the intersections with complex lines on your zero set. So you just intersect Z of P with a complex line, then this will have exactly D zeros, and then you move with the action of UN plus 1 all of these projective lines, and you get back to D. Anyway, so the important point is that the volume is just the degree times a factor that depends on the dimension, so it does not depend on the polynomial itself. As I was mentioning, indeed, in the case n equal 1, the volume is just the number of points. That would be the number of zeros of a polynomial of this form here. Okay, here, this one, I dehomogenize the polynomial, but it's just the same thing. So it's just the degree. And then, okay, you have a polynomial in the case in which it does not belong to the discriminant, you can associate, we understood that the normalization factor does not depend on the polynomial itself, and therefore a natural way to associate a probability measure to each polynomial is just take the volume measure, this is the one induced by seeing Z of P as a submanifold, and you just normalize it by the factor that you have, okay? So this will be a map from PND to the space of probability measure over CPN. And the expression just means that what you do as a probability measure, just integrate on the zero set, okay? And here I just also want to mention that also PND, so the space of homogeneous polynomial, if you see it just as a space of parameters, can be seen as a linear space actually, okay? So PND itself, so the space of homogeneous polynomial, has a natural structure as a linear space of C of the proper dimension, okay? So in this case, so PND can be seen really like just a linear space. And here, what we have, you have this map here, mu, that we will call the solution map, that will go to the probability over CPN. And here, to each single point, we associating, let's say, its zero set, okay? It's a probability measure over the zero set. And the reason why I draw this picture is because here on PND, if you identified with a, let's say, a C of, let's say, K with K, the one that I've written there, the geometry, it's not so interesting because somehow you're just realizing the space of homogeneous polynomial just like any linear space, okay? So there is no way to distinguish between, let's say, the space of polynomials with its own structure with respect to any other linear space. It's just the classical distance that you would put on an ECN, okay? Okay, so the first thing that you want to do, you actually do not want to define this map, so this solution map only for the regular polynomials, but also for polynomials possibly having a singularity. And the first thing that we have done, so we extended this map anywhere, so also for maybe polynomials having a singularity. So maybe if you have here, if you want to draw something like this, maybe also for polynomials of this form here. And it turns out that you can extend this map in a nice way. And it turns out to be a weak star continuous if you put, so it's just an homeomorphism once that you put the weak star topology on the space of probability measures, okay? So here, maybe it's a good remark to say that it's not so trivial the fact that if you have somehow a map from the space of parameters and you are somehow taking a measure valid map, it's not understood that you will get immediately a continuous map. If you want, you can also think about the fact that you are considering, if you want, a map that associates a T, let's say a measure concentrated on the level set of Ft. Okay, F at time T. Obviously, it depends so much on F. Maybe F is injective, at some point becomes a line. So it's you have to use something on the structure of this map. And okay, so you again to overcome this issue, what you do, you somehow again intersect with lines, and you can use the concept of multiplicity. So when you have, say, if you are in dimension 1, the polynomials belonging to the discriminants are those with multiple zeros, okay? So you have maybe two Dirac deltas arrive at single zeros, then there you want to extend this map also on those points, and what you have to do, you have to just count those zeros twice, let's say, okay? If you just have to Dirac arrive at one point. And the same concept you can, let's say, introduce also in a multidimensional setting, and using this kinematic formula that I've shown you before, you restrict yourself to dimensional arguments, and you extend this map also to possibly singular polynomials. So in the end, the idea is that in the end we arrive at a well-defined map from the space of polynomials into the space of probability measures over CPN, that at each polynomial associate its volume measure with possibly using this concept of multiplicity, and this is a continuous map that it's an homeomorphism onto its image. So it's invertible and everything. Okay. And so the reason why I call this map the solution map is indeed because it's the map. If you want to, again, go back to the dimension one case, you have, in the case in which you have just univariate polynomials, so means that just when one variable, our map mu is the map that associates to, let's say, a list of coefficients, so that it's the one describing your polynomial, the set of 0 deltas, so of the deltas on the roots, counted with their multiplicity. Okay, so this coefficient here is just the multiplicity of the 0. Obviously, the inverse map would be the easy direction of this construction, means that you have the zeros, you just then cook up the coefficient just by doing the multiplication of the monomial exactly with those zeros. So this map, it's somehow a little bit more interesting because you won't like to, let's say, what you have in the end of the polynomial are not the zeros, but the coefficients, okay? And on the metric side, if you want to, let's say, introduce a distance here on the roots, the classical thing that you can do to measure the distance on the roots of this form here, what you have to do, you just have to somehow let's say, identify a measure of this form with the symmetric product of C of the symmetric product of C times D, okay? This means somehow that you are considering D copies of C and then you just neglect the order, okay? And let's say for D points of this form here, a natural way to measure the distance just to consider that Wasserstein distance if you want, or just the natural distance you would put on the symmetric product of C, okay? So let's say in dimension one is already very clear what you do in this setting. And also, let me also make an additional comment. The best that you can hope from this map is that is to be Holder continuous. Indeed, you can just think of a very simple example. It's just take z to the d minus t. So t, it's moving, it's just a coefficient, real coefficient. And if you look on I mean, where the zeros will be, they will just go to 0 with the power 1 over d. So the regularity, so that this map mu will not be better than Holder regularity, Holder regular, okay? When you approach the discriminant, because you have this d root appearing. Yes, exactly. Okay, now the plan is that we have moved each of these polynomial inside the probability space over CPN, and now we want to introduce a Wasserstein distance between polynomials, okay, just by taking the image of mu. So again, when mu is equal to 1, this is already clear, and the reasons that somehow when you have, let me just write like this. So in the case n equal 1, the image of mu, it's you just have, let's just draw, let's say mu of P naught will just be a bunch of Dirac deltas. And then if you have mu of P1, well, actually this is color, it's very similar. I don't know if you can distinguish between colors. So anyway, if you have two probability measures of belonging to the image of mu when the dimension is equal to 1, then what you have to do, you can just do the classical optimal transportation problem. You will have a matching between the purple dots and the white dots, let's say, like this, and you just do the interpolations and you have no issues at all. And the reason is because the image of the map mu is just geodesically convex. Okay, if you have Dirac deltas, you move them, they are just so you just do the matching problem, and then the Wasserstein geodesic just moves along lines, and in this case they still belong to the image of the map mu. For the same degree, yeah, this is always fixed. Thanks. When n is larger than 1, then the image is not anymore geodesically convex. So you might have that you were starting from a linear space, and then maybe the image will be something curved. So this will be mu of P and D. And then possibly if you have, let's say, two mu of P naught, mu of it might well be that the Wasserstein geodesic goes out from the image of the embedding mu. And therefore, I mean, we all very well what we have to do in this case, we have to consider the induced length, so the induced geometry, by seeing the image of mu as a subset of the space of probability measure, and consider the induced length structure seeing as on a subset. Okay, so not maybe this slide, it's very well known to all the experts in the audience, but anyway, let me just mention that in this case, how do you go? You take, if you have a metric space, you take AC2 curves. This means it's just a definition of being AC2. So it means that there exists a function, it's NL2, such that the distance between gamma t and gamma s is bounded both by the interval between s and t of mt. And then in this case, if gamma is in AC2, we associate its metric speed, and then we define the energy like the L2 integral of the metric speed of the curve. The metric speed, the metric space is called length space if you can recover the ambient distance by taking the infimum of this energy. And if the inf is a mean, then the space is called a geodesic space. And obviously, we know by Benamou-Bernier formulation of the W2 distance, the Wasserstein space is a geodesic space as well. And therefore, we want to use this geodesic property of the space of probability measure over CPN to induce a length structure over there. And therefore, now we can somehow answer the original question, so how to deform via optimal transportation a polynomial into another one. So the first thing to do, you take the admissible path, so that a priori it might well be that you have no admissible path at all. So what are the admissible paths? So this will be the curves from the interval in the space on our space of parameters, that is just P and D. So we have here we have P naught, here you have P1, and here you consider all the curve alpha, such that once that you move here, so here you have mu composed with alpha, and you want this path here to be AC2 in the Wasserstein space. And then you define the inner Wasserstein distance between P0 and P1, as you would imagine, by taking just the infimum of the energy, when where now this metric speed here has to be understood as computed inside the Wasserstein space over CPN. Okay. And obviously, this fact that you put here inner really means that you are inducing the length and taking the inner distance induced by length structure of CPN, compared with this outer, classical outer Wasserstein distance. Okay, so the first question, obviously, so far nothing special, because it's it's everything more or less standard, meaning that this is a classical construction. You can, once that you have a subset that it's not convex in a geodesic space, you just induce the length structure, you minimize among the curves living inside your set, and you hope to get something meaningful. So now you will have somehow to overcome two main issues. The first one, you want to be sure that actually this set here is non-trivial, meaning that actually is not empty, that it's not clear, and also that the inner Wasserstein distance that you would get, it's not zero or plus infinity or trivial. And so to answer these two questions, so we try to see how to compute this energy. So we started from a curve of polynomial that do not meet the discriminant. So meaning that maybe the discriminant, let's do it like this. So this is delta. Yes?
Set is a manifold.
Yes, it is a submanifold. Well, it depends on the terminology, yes, but you could have, for instance, if you have a polynomial that is defined as smooth submanifold, if you take the polynomial squared, it anyway belongs to the discriminant, because now the discriminant for us is the equation that it's singular. It might well be that it's, it contains many different things. But yeah, in principle, it might have some kind of, it will be a stratified object, the one that you would get. Maybe you have intersection and... Okay, so now we have, let me draw another picture. So now the picture that we have in mind is the following one. So we have the discriminant, let me write it like this. Now we have P0, P1, and here we have our starting object, our final object. We have this curve here, alpha, that will be moved above by doing by doing this interpolation like this. And the key object to, I mean, at least on the technical side, is that if you have a curve that does not meet with a discriminant, then actually you can prove that all of these zero locus, they can be mapped from one to the other via what is called an Hamiltonian isotopy. That is this map here, phi t, that it's a map from CPN to CPN. And the fact that it's an isotopy means that it's a smooth family of diffeomorphism. So it means that at time t equals 0 is just the identity, and at time t, it just pushes you the initial zero set to this zero set at time t. So here we are inside CPN here, and here at time t equals 0, phi of 0 is just the identity, and at time t it arrives here, let's say, okay? And also the fact that it's Hamiltonian means that if you consider the fields, the vector field generating the isotopy, then the vector field is induced by, it's Hamiltonian, okay? And in particular, this means that these fields, that this isotopy preserves the volume form. So this means that the push forward of the map mu0 at time t will just be precisely mu1. And this permits actually to compute very well the L2 metric speed of this family of maps. Indeed, what you can, I mean, we managed to compute explicitly the metric speed of this object. It turns out to be of this form here. Okay, so let me maybe just do a quick comment on how we get to this formula here. Sir? No, Hamiltonian means that it means that the vector field is induced by a function. So it depends on phi t. So here you have a symplectic form that is inducing your vector field, but so the vector field is the Hamiltonian vector field associated to the function phi t. Yes, the symplectic form is the standard one. Yes, of CPN. Yes. And why this one is rather important, because here you have to, if you go back to the pictures of having a submanifold with a volume measure that it's evolving, for those experts that knows a little bit about how to compute the metric speed, here somehow what you have to do, you have to do a decomposition on the tangent, on the space of gradients. And in this case, the space of gradients will be a space of gradients on the tangent space of the submanifold plus any direction that you want to get on the normal component of your submanifold. This is by a result, I think, I don't want to miscite anyone, but many people in the audience worked on this. So also Sinichi and Nicola and also Robert, I think. And so if you want to compute, let's say, the metric speed of this measure mu t, what you have to do, you have to look for the projection of this vector field vt on this space of gradients. The space of gradients, in this case, when you are moving a submanifold of certain codimension, is obtained by doing the space of gradients on the tangent space plus any direction orthogonal to the movement. Since the vector field is Hamiltonian, the tangent space, once that you project on the tangent space, you will get something that it's orthogonal to the space of gradients. So you just see the orthogonal direction. So in the end, what we obtain by doing some calculations using the very specific structure of CPN, you end up with this very nice expression of the energy. And so I think also, let me do some comment on the shape of this energy. What you will see, so the relevant object is this one that you have inside. So you are integrating over the zero set of the polynomial, and you are integrated, okay, the time derivative of the coefficients, so just it's an expression just of the coefficients of the polynomials, and you divide it by the gradient p squared. So in some sense, what is happening is that if you are arriving to the discriminant, somehow you are exploding, no? Because on the discriminant are those polynomials on which you have zero set, and also the gradient annihilates. So the intuition is that somehow this energy somehow should avoid the fact that you are going through the discriminant. Should force you to remain away from the discriminant. Okay, so as a consequence of this result, we prove that the space of admissible path is non-empty, because we constructed explicitly a way in which you can go out from the discriminant, because now that you have an explicit expression, you can, let's say, cook up a way for going outside from the discriminant with finite energy. So as a first non-trivial consequence, so this distance is non-trivial. And we had, let's say, a list of properties of this W2 inner distance. So the first one is that obviously you get a complete and separable geodesic space. Now you have to always understand that P and D here. So now we are, let's say, moving the Wasserstein distance on the space of parameters, that it's the space of homogeneous polynomials, okay? So P and D, remember, as the space of polynomials induced with this Wasserstein distance induced by this immersion map. So it will be a complete and separable geodesic space. We have actually that is complete metric is induced by an Hermitian metric away from the discriminant. And in particular, that it's the Hermitian metric is exactly the integrand that we have seen before. So in particular, moreover, what you have that is this Hermitian metric has a closed imaginary part. So it means that with this structure, the space of polynomials turns out to be Keller. So in a way, the Wasserstein distance is inducing a Keller structure on the space of polynomials. And now, obviously, what we have in mind, what we would have expected is that also to obtain a compact metric space, but so far we didn't manage to prove it. I mean, it seems very easy to prove it, but it's actually very hard. So this will be actually one of the open problems that I will list at the end. What we managed to prove is that this space is actually compact only if you are far away from the discriminant. So let's say that we define P and D epsilon at the space of polynomials that are at Fubini study distance from the discriminant more than epsilon, then the map, let's say, associating to P and D with the Fubini study distance to the Wasserstein inner distance is Lipschitz, and in particular, P and D is compact. This is to say that the two Wasserstein distance is comparable with the Fubini study one. Yeah. Well, actually, because yes, you're right. Sorry. I mean, P and D is actually, you have to see it as the projectivized of the one that they have written at the beginning, because actually here we are working with I've been a bit sloppy here, so we are working with the projectivization of the one that they have written at the beginning, because a polynomial and its multiple just define the same zero set. So if you want to have an homomorphism, you cannot work directly with P and D, but you have to make a quotient, and therefore the Fubini study is always something that you put on the quotient once that you make this, let's say, identification up to a multiple of C. Okay, sorry. Thanks for the remark. Okay, concerning this last point, as I said, it's non-trivial. So what we have a compact, I mean, the picture. So why this compactness is non-trivial? So now we have a compact ambient space that is P2 of CPN, that is compact because CPN is compact, and we have a closed subset. And I'm saying that the induced metric on this closed subset might well be be a non-compact set. And you can always have to have in mind this example of the square that is obviously compact, and you take as a closed subset, let's say, these lines that are approaching the horizontal line, and this one with the induced length structure. This will be again a closed subset, but it turns out that all of these points are at a positive distance, and this will be a non-compact subset. So actually, this last point took us really a lot of time, and we didn't manage to obtain. Okay, now let me go to the last part of the talk. Let me actually first do this summary. So we have introduced this Wasserstein distance on the space of polynomials. It turns out to be a Keller structure over this P and D. And let me go to this application. So I just want to spend a little bit more of time on this second application. Then if time permits, I will go back to the first one. So the second application concerned what is called the Smale 17 problem. And the Smale problem says that, the problem that he posed was to find an algorithm that finds the zeros of a given polynomial in a polynomial time. Okay, so this was the way in which the question was formulated. Actually, it was formulated for a system of polynomials, and you want to find, let's say, given a system of polynomials, find a zero of that polynomial in polynomial time. And this, yes? Okay, the way in which the problem was stated was very vague. So then people started to address in even more generality, but you can think about of being a polynomial in any variable, and I want to find it in the okay. There is a well precise definition to find a polynomial. So on average, you want to approximate the polynomial. You do not want to find it exactly. Okay. Sorry, I didn't get it. The zero. You want to approximate the zero of the polynomial. Okay. No, it's complex. Complex polynomial. And this has been, okay, actually has been solved already. So, there was a little bit of hype on this problem, but actually this has been solved, sorry. Has been solved by a list of people, and by in even higher generality, by a serious contribution by Beltran, Pardo, Hugenburgis, and Lere, finally. And so the strategy that they have been used is this following one, is the so-called homotopy method. So what you do, you start from, you have a polynomial of which you would like to find the zero. Here I'm doing some confusion because this Smale formulated the problem for a system of polynomials because he had in mind the fact that you want to find exactly, let's say, a zero. That is, once that you have a system of polynomials, you get just a zero, not a submanifold. But now let me just make some, be a little bit sloppy and just think about just a single polynomial. So you have here the polynomial P1 of which you would like to find the zero in this polynomial time. You start from another polynomial P0 of which you know the zeros, let's say P0. So this one is the one given by the problem, this one is the one that you pick because you already know a zero of P0. And then what you do, you take an homotopy from P0 to P1, that this would be just the linear interpolation. This would be P. And then what you do, you just prolong the zero of P0 via the Newton method. And you just study how to, let's say, continue the zero of P0 until P1 via the Newton method. And from dimensional consideration, you can find this homotopy that does not intersect with the discriminant. This is because the discriminant has codimension 2, as real codimension 2, so you can always, so it is not disconnecting your space of parameters. And I mean, what has been, let's say, observed in a series of papers by Schub and Smale is that the complexity of the algorithm, let's say, so how much it is costly to run the algorithm, is exactly how far away PT is from the discriminant. Okay, so if PT is approaching the discriminant, the cost of the algorithm is exploding. And this is the distance of PT from the discriminant is what is called the condition number. And therefore, okay, so these people solve the problem by, let's say, choosing in a very smart way P naught. Okay, so if you are very good with choosing P naught, in the end, what you can do, you can let's say perform this Newton method in a polynomial time under some additional assumptions on P1. However, the initial idea of Schub, that was actually much before the solutions via this other method of this list of people, was instead of using linear homotopies, why don't we use a certain class of well-behaved curves? So instead of considering a classical Fubini study metric, what you do, you just penalize the distance from the discriminant. Okay, so you introduce what is called the condition metric. You have an obstacle that you want to avoid, and you consider as a new metric 1 over the distance from this from the discriminant squared times the ambient measure. And what Schub prove is that the Newton steps that are to continue a path the Newton steps needed to continue the zeros along this new path that is avoiding the discriminant goes like the length of the path that you have selected, so this condition length of the polynomial that you have selected. So what you have here, you have, let's say that we call this the discriminant. You want to, let's say, max. Okay, let me do it maybe like this. You want somehow to penalize as much as you can the proximity with to the discriminant. And Schub proved that, okay, if you have an upper bound on the condition length, that is just the length with respect to this condition metric, then you are able to solve Smale 17 problem. The obstacle to let's say to running this program by Schub was indeed to find an upper bound on the condition length, because I mean you have defined a new metric, but then you have to be able to indeed estimate how close you are to the discriminant. And the conjecture again by Schub was, okay, is to prove that the logarithm of the distance squared minus 2 to the discriminant is convex along condition geodesics. So this means just that the maximum of the the minimum of the distance to the discriminant is just reached at the initial or the final point. And this again has been solved under some additional conditions that are not verified in general by the discriminant. This list of people, Beltran, Didier, Malajovic, and Schub, proved that if you are, instead of taking the discriminant, take any C2 submanifold, its distance, so that you consider the same kind of metric, so the condition metric with respect to this obstacle that is a C2 submanifold, then this Schub conjecture holds true, but they didn't manage to prove it in the general case. And in the end, what it turns out that at least in the case n equal 1, the language of optimal transport suits very nicely to this with this problem, because okay, here let me just go back over here. You see that there is a very strong link between this condition metric introduced by Schub, so you want to penalize the proximity with the discriminant, with our metric that is the one induced by the optimal transport problem. So let me just go back here. Let me go back here, maybe even here. So because you see here what we are integrating is just not, so it's like if we are integrating, so it's kind of, if we are having, let's say, the L2 version of the Schub distance, okay? So we just discovered it after, I mean, we arrived with this metric. So here we are penalizing as well the proximity with the discriminant, and therefore we manage, at least in dimension 1, to prove exactly this kind of estimate. So we prove that if you are taking W2 geodesic for these polynomials, then the proximity to the discriminant it's controlled by the proximity of the initial and final point. And yes, the quasi-concavity is that you do not really have concavity, but you have 1 minus t squared and t squared in the concavity condition. And it turns out that if you want then to arrive at this kind of estimate, you have to plug some strange exponents in the beginning, in the expression. But anyway, I mean, in the end, for the flavor of the result, to find an upper bound, the condition length, this is more or less it's more or less equivalent. It's not, yeah. Okay, I conclude with two open problems. So the first one, as I said before, is the compactness of our space. We were not able to prove it. And I mean, only the positive for n equals 1, because this we know that it's, I mean, it's just the symmetric product of d copies of C. And in the higher dimensional case, I mean, here what we have to discuss is actually that this is a metric on the space of parameters, okay? But if you look on the literature, there are examples on which metric induced of this type, they are called the Weil-Petersson metric that I haven't discussed, but more or less they have the same kind of structure. So in the space of parameters, like the Muller space, then you will end up with a non-compact space. So it might well be that the space of polynomials with this inner Wasserstein metric to be non-compact. But yeah, so far we have no guess. So, and the other very interesting problem for us, at least that we didn't manage to overcome, was to prove the geodesic convexity of the complement of the discriminant. And also, actually, for this one, we expect this one to be true, because we have seen that our energy penalizes the fact that you are approaching the discriminant, because you are integrating 1 over the gradient of p squared. But yeah, in the end, also, we didn't succeed here. So it's a bit frustrating, but it's, yeah, we tried a lot, but we didn't prove it. And I mean, it was known just for n equals 1, just because here you have a bunch of Dirac deltas, and this you already know the answer. Okay, I think that my time is over, so I finish here.
So thank you very much. We have a few minutes for questions, comments. Ah, ok, allora lo fa girare lei.
La prima. Chi vuole essere il primo?
Grazie. Okay. So with respect to the computational model of Blumenschub-Smell, where you have a Turing machine with the possibility of performing plus and times of real numbers in one step. So my question is, this problem of posed by Smale and now solved, does it give some advance on the structure of computational classes in this? Because I think that in this model, funny things appear. I think MP could be also equal to the recursivity enumerable. So is there any progress in solving this question of Smile?
Well, I have to admit my complete ignorance on the, I mean, our point of view. I mean, the papers that I've mentioned before are very technical, and for me, were very hard to go through. So I mean, my understanding was very superficial. Our point of view was that their method was by hands. There was some issues with this Shub approach, considering the condition length. And our focus was on reinterpreting Shub condition metric as a Wasserstein distance. This was our, so the Shub condition length is the W2 distance between the polynomials. And the reason why we believe this is interesting, I can bring a little bit more to the problem, is that now becomes a problem of regularity. Because now if you know that some strange phenomena, like for instance, in the case n equal 1, you are far away from the discriminant because there is cyclical monotonicity that kicks in, and you know that you cannot have crossing and anything like this. So we expect locally that you might get the same kind of approach, but we don't know how to do it. And once that you prove that you avoid the discriminant, then maybe you are also able to prove that you can bound the proximity to the discriminant with the proximity of the initial and final point. But also let me mention that we did not go through the computational cost of following a Wasserstein geodesic. So maybe we are somehow proposing a different point of view, but without saying that our approach would be less costly than the one that they are following. So this is also another project that we had in mind to do, like to see how much it is cost to follow this vast geodesic with this metric that we have introduced, but on which we haven't answered yet. So I guess I've not answered your question, but yeah.
Question?
Just a comment on the question.
Okay, maybe there is an expert in the
So it's just a comment on the question. No, I'm not an expert on this, but I know the difference between complexity classes in computer science and what is meant in these kind of analysis questions by solving something in polynomial time. Because here there's always an accuracy prescribed. So there's a kind of epsilon, and the goal is to solve the problem within an accuracy of epsilon, where the time has to scale polynomial in 1 over epsilon and the parameters of the problem. And so that's different from working in exact arithmetic and looking at P versus NP in discrete math. That's a different world. It always means polynomial time in 1 over accuracy.
So assume that P and D is not compact. Difficult to believe, but assume it is. What do you expect the compactification could be?
That's a very interesting question. I have no idea, actually.
It's complete.
It's complete. I guess I have no smart answer to this, to your question. Yeah, I have to think about that. I don't know.
Okay, I think now we have to make a short break before the next talk. Let's thank Professor Cavalletti again. We'll talk about optimal transport methods in metric Sobolev theory. Grazie.
Thank you for the presentation, and I would like to thank the organizers. Yep. I would like to thank the organizer for the very kind invitation. It's a pleasure to be here. So I will begin with So we'll begin with a outline of my seminar. So I will talk about analysis in metric measure spaces, and more specifically, I will discuss different notions of first-order Sobolev spaces in this setting. So there have been several different, a priori different approaches to this topic, and I will focus on 3 approaches. So I will discuss a notion that I will call AH1P. So you define Sobolev function in metric measure spaces by approximating with Lipschitz functions. Another approach is by looking at the behavior of functions along suitably chosen rectifiable curves. And the third approach is the integration by parts, where you use some sort of vector field in this setting that is called derivation in the metric setting. And once you have constructed this different notion of Sobolev functions, you can also develop a vector calculus. So you can also talk about vector fields and one forms, even in this setting that is possibly non-smooth and infinite dimensional. And the important point is that I will show how optimal transport and convex analysis techniques play a very important role in proving the equivalence between all these approaches. So to sum up, I will present several well-established results in this field. I will tell you something about some recent new results about it, and I think the goal is to show that one of the possible ways to show this equivalence result is through the lenses of optimal transport and convex analysis. So this is the main goal of my talk. Okay, so let me now give you fix the setting. So I will take an exponent P finite, and I will always denote by Q its conjugate exponent. And then I fix a metric measure space. So in this talk, by metric measure space, I mean a complete and separable metric space together with a Borel measure that is finite on every bounded Borel set. So I would like to point out that first point is that I am allowing for the exponent p equal to 1. So this is one of the novelties we present today. So most of what I will tell you next works also when the exponent is equal to 1. And then I also would like to mention that I will stay in this setting with this notion of metric measure space for the sake of presentation, but some of the results I will present hold in a greater generality. So they hold even for metric spaces, neither complete nor separable, but assuming the measure you consider is a radon measure. Okay? So this has application, for example, if you want to study these when you consider domains in some complete space. Maybe the domain is open, so it's not going to be complete, maybe, but still you can prove equivalence of some of these notions. Okay, so next I will give you some introduction to the notion of metric Sobolev space I will consider. So let me begin with the first approach, that is this space that I will call H1P. So you declare that a LP function is in this space if you can approximate it with a sequence of Lipschitz functions that are boundedly supported in such a way that the asymptotic slopes of this function converge to some limit function in LP. So the asymptotic slope function means that at every point you are associating the asymptotic Lipschitz constant. So you look at the Lipschitz constant on a ball of some radius r, and then you let the radius goes to 0. Okay, so infinitesimally you look at the Lipschitz constant around this point. So this asymptotic slope plays the role of the absolute value of the gradient if you consider like a smooth function in a smooth setting. Okay, so since we are in a general metric setting, you replace a smooth function with a Lipschitz function, and you replace the modulus of the gradient with the asymptotic slope. Okay, so this is the definition, and it's possible to select a minimal almost everywhere function that is called the minimal relaxed slope. So it's minimal both in the integral and in the pointwise sense. And once you have selected this minimal object, you can define the so-called Chigger energy functional. So this is essentially the Dirichlet energy in the metric measure space setting. So you can represent this energy in via this integration of the minimal relaxed slope to the power p. And this is called usually Chigger energy because this approach was introduced by Chigger 25 years ago. And his definition was a bit different, so he was considering upper gradients instead of the asymptotic slope. This specific definition was introduced by Ambrosio Giglia-Savarin. And okay, this is what I wanted to tell you about the first approach. Now, the second one is when you look at the behavior of functions along curves. So I will actually define two different spaces, N and B, but following the same kind of principle. So roughly speaking, definition of this kind should look like the following. So you declare that a function is Sobolev if you have the following property for almost every curve gamma, and I will tell you next what means almost every curve. You can look at f composed gamma, and this is an absolutely continuous function. And there is some function g in LP that is bounding from above the variation of f composed gamma. So the derivative of f composed gamma at t is smaller than g at gamma t times the metric speed of the curve for almost every time t. Okay, so this is like the general, quite rough formulation of this sort of condition. Now the important thing is to say what it means almost every curve. So we need to fix some notion of negligible sets of curves in order to give a meaning to this. And there are also other issues, for example, how to show that this is independent of the representative of the function. There are several issues, but I will give you some sort of informal description of this. So the first approach is what is called Newtonian Sobolev space. So here, when you declare almost every curve, you declare this notion of negligibility, you use the p modulus. So the definition of p modulus is the following. So you take a family of curves, gamma, and you look at the infimum of the integral of rho to the power p, where rho is a competitor, is an admissible function, which means it's an LP function, such that the path integral of rho over every curve gamma in our family of curves is bigger than or equal to 1. Okay? So this can be defined for any family of curves, and this, in fact, defines an outer measure. So this is not a regular outer measure, but it's an outer measure on the set of curves. So this approach was pioneered by Fuglede in 1957 in the Euclidean setting, and then later it was extended by Shanmugam in the setting of metric measure spaces. And the formulation of the modulus is exactly the same for the Euclidean setting and for the metric setting. Okay, so once you choose this, okay, you take this P modulus, and now almost every curve means almost everywhere with respect to this outer measure. And this gives you, with sort of the definition above, gives you the space N1P, the Newtonian Sobolev space. So technically speaking, this is usually defined by taking functions and not equivalence classes, but okay, I will not say much about it in the talk. Another approach is what we can call Beppe-Levi Sobolev space. So in this case, almost every curve means for pi almost every curve, for every pi that is a dynamic plan with Q barycenter. So what is it? So it's a dynamic plan with Q barycenter is a finite Borel measure on continuous curves that is concentrated on rectifiable curves, and for which you have the existence of a barycenter that is in LQ and also in L1. So barycenter means that if you look at the superposition of these path integrals with respect to the plan pi, you can represent it as a function in here that is an LQ function. Okay? And this barycenter is uniquely determined by this formula. So the first, okay, so in this way, we get a notion of almost every curve in this specific way, right? So for every plan with barycenter, the condition holds for pi almost every curve. Okay, the first definition of this kind was a bit different. So it was defined by Ambrosio, Gigli, and Savaret. And the first definition was using another notion of plan of curves. So the first notion was using test plan, that is a smaller class of plans, of curves. And this specific notion was introduced later by Ambrosio, Di Marino, and Savaret. And it was used by Savaret to give, to define a Sobolev space in this setting. And I decided to present the definition with this notion because it has some nice duality properties that I will illustrate later. Okay, and so also here, once you have fixed now this notion of negligibility for curves, you get, via the weak upper gradient condition, you get the space B1P. So also in this case, you can select the minimal G. So in the weak upper gradient inequality, you have a function G. You take the minimal one in the almost every sense, and I will denote it by dfn when I'm looking at a function in N1P, and the same for B. Okay, and finally, the last definition is the following one. This approach, the integration by parts formulas, was introduced by Di Marino. So what we mean by Lipschitz derivation is a linear functional B that is defined on the space of boundedly supported Lipschitz functions, taking values into L1. So this function is giving us a function. So roughly speaking, if you look at B applied to F, you can think of it as the differential of F times B. Okay? You cannot do it in the smooth setting, but this is a way to give a meaning to nabla F times vector field B. So we have two requirements for a Lipschitz Q derivation. So the first one is the Leibniz rule. And the second one is this sort of weak continuity property. So we assume that there exists an IQ function H for which you have this pointwise almost everywhere bound. Okay. So notice that here I'm taking Q that is the conjugate exponent to P. And the reason is that I will define the Sobolev space by duality with these objects. Okay, and once you have this pointwise inequality, you can select the minimal function H in the almost every sense. And the minimal one I will denote in this way. So it's called the pointwise norm of the derivation B. So it plays the role of the pointwise norm of the vector field. So now we have defined this space. I will denote it by der Q. So this is the space of all Lipschitz Q derivations. And this is a Banach space if you just integrate the pointwise norm. And it's also a module over L infinity. So it's easy to see that you can define multiplication of this derivation by L infinity functions, and you get a module, the algebraic sense. So we have these two structure. But if you want to define Sobolev spaces using these, we need to take a smaller class of derivations that is suitable for defining Sobolev space. So we need to look at derivations with divergence. So we say that LP derivation has Q divergence, LQ divergence, if the following holds. So you can find a LQ function called divergence of B, for which this integration by parts formula is verified. And as before, also this divergence is uniquely determined by this function. So now we have selected a subclass, a subfamily of derivation that I will denote by der QQ. So the superscript exponent indicates the integrability of the derivation, and the subscript indicates the integrability of the divergence. So you can give a very similar definition when, okay, here I define it only when divergence is a function. You can also be a measure, so that this formula makes sense. Okay. Later I will consider also derivation with measure value divergence, but the definition is pretty much the same. So now we have this subspace. It's no longer an L infinity module in general. And the reason is that if you multiply by an L infinity function, you might lose the effect of having divergence. Nevertheless, it's a Lip submodule. So you can multiply by boundedly supported Lipschitz function, and you still get a derivation with divergence. Okay, once you have given this definition, you can define what is the Sobolev space by duality. So you declare that an LP function is in W1P if you can find a linear operator defined on der QQ, taking values in L1, satisfying essentially the same as before. So you have this sort of weak continuity property, and you have the desired integration by parts formula. Okay, and again, you can select the minimal function G in the almost reverse sense, and this turns out, I mean, this is what we can call the minimal weak upper gradient of the function f. So this is the minimal function associated with our Sobolev function f. Okay. So these are the definitions that we will consider. And now I will present the main result in this talk. So all these approaches are equivalent. So here I collected, okay, so there are many contributions that were needed in order to prove this theorem. Here I collected all of them in a single statement. So you take an arbitrary metric measure space, you take an exponent p, possibly 1, and all these spaces are exactly the same, and the minimal weak upper gradients and minimal relaxed slopes are also the same. So I try to keep track of all the different contributions to the proof of this equality. So I will try now to tell you something about the history of this result. So first proof was under extra assumption by Chigren and Shammugalingham. So they work in the setting of so-called PI spaces, so like doubling metric measure spaces, satisfying some weak Poincare inequality. And what they proved in that setting is that H is equal to N. But I would like to focus on arbitrary metric measure spaces without these extra assumptions. So the very first proof of the equivalence in the general metric measure space setting is due to Ambrosio, Gigli, and Savaret. So they proved that H, N, and B are the same with the same weak upper gradient for every exponent p that is strictly bigger than 1. And this proof used the metric of flux semigroup. And in fact, they proved something even stronger where, I mean, they defined the space B using test plan instead of plans with barycenter. And then later, Simone Di Marino introduced the definition using derivations. And he proved, again, when p is bigger than 1, that it's equivalent to all the others. So he basically proved that W1P is squeezed in between H and B, and then he deduced equivalence thanks to the previous result. So that's why he was, I mean, that his proof works when p is bigger than 1. Later, there was another proof of H equal to N equal to B, again for p bigger than 1, that is due to Giuseppe Savaret. And the proof is somehow different. It relies on von Neumann-Mimax theorem. And he was proving some representation formulas for the dual energies that are involved when you consider these functional spaces. And the proof is somehow different and is using, I mean, it works in the more general setting of extended metric topological measure spaces. So I will not focus on this class of spaces. I would just like to say that it is a larger class of spaces that contains metric measure spaces in the sense I was telling you before, but also some infinite dimensional structures like the Wiener space. So the idea is that instead of distance, you have an extended distance that might take values plus infinity. But most importantly, the point is that you can distinguish between the metric and the topology, in the sense that the measure you consider is defined on the Borel sigma algebra of a topology that is weaker than the one induced by the extended distance. Okay? So this allows for a lot of flexibility, and this has some interesting consequences also in the setting of metric measure spaces. And then, okay, I would like to mention another result I have in collaboration with Danka Lucic. So we proved again the same, h equal to n equal to b, and again for p bigger than 1. And I wanted to mention it because there are a few ideas here that I will present later in the talk. So in this proof, we basically reduced the problem to a problem in Banach space setting. And philosophically, it's somehow similar to the proof by Savary using the max principle. But all these results work when p is strictly bigger than 1. And roughly speaking, what happens if you take p equal to 1? What happens is that similar techniques for p equal to 1 can be used to prove equivalence of BV spaces. So you can also define functions of bounded variation in the metric setting. And all these approaches will give you equivalence for BV spaces and not for Sobolev spaces. Okay, and this has been done, for example, by Ambrosio and Di Marino, and also other papers. While if we want to prove the equivalence of Sobolev spaces for p equal to 1, we need another strategy. And the first result in this direction is due to Sylvester, Eriksson, Biquet. So he proved that h and n are the same even for p equal to 1. So in a sense, his approximation is more, say, direct. I don't know how to say. It's like more a metric approach. So while the previous approaches are like functional, and then for p equal to 1, they don't work for the Sobolev space, this is a more direct approach. It's some sort of discrete convolution. And this works also for p equal to 1. So this was the first equivalence result when p is 1. And finally, in a work in collaboration with Luigi Ambrosio and Toni Konen and Danka Lucic, we completed the proof of this identity for every p. So what we did, in fact, is we proved that B11 and W11 are the same like the other spaces. This was the missing point. So with this, we can close the circle about these equivalence results. Okay, and okay, this was like an outline of the literature about this topic. Next, I would like to tell you some details about this equivalence, but actually I will focus on the case where p equal to p is strictly bigger than 1. Okay. So the first, it's not visible. Okay, so first of all, I would like to distinguish, to prove the equivalence between h and w. So what I'm going to tell you is essentially containing a work in progress with Janne Taipalus. And we have a new proof of the equivalence between h and w. And actually, the argument is rather general. It is a duality argument that works in greater generality, in a sense. So it has little to do with the geometry of the spaces that we are considering. So first inclusion was already known. So how to prove that h is included in w? So this was done by Di Marino already. So you start with a function in h1p, and you want to show it's in w1p. So you fix a derivation with divergence, and you want to define the linear functional L of f. Okay, so you take an approximating sequence of f such that the asymptotic slope converges to the minimal relaxed slope of the function. So you just apply the definition. And then it's possible to show that Bfn have a weak limit in L1, and this is our definition of Lf applied to B. And then you know that Bfn is smaller than the pointwise norm of B times the asymptotic slope. You just pass this condition to the limit, and you get the desired one. So once you have constructed this function explicitly, you just check that everything works, and at the end, you end up showing that f is W1p, and you have this pointwise inequality between the minimal objects. Okay. So the novelty I will present now is the other inclusion. So now I will show you that W is contained in H, and this is somehow a new idea inspired by a paper with Danka. So the argument is the following. So, okay, now we take H as a starting point. This space induces a linear differential. I will not give you the details now because we just need a little bit of this theory, but Nicola Gigli proved that once you have this Sobolev space, you can define an object that is called cotangent module. So it's a Banach space with some additional structure. And you can define a linear differential defined on the Sobolev space, taking values in this Banach space. Okay? So for what I'm going to tell you next, the only thing we are interested to is to know that the Cheeger energy can be expressed in this form. So the Cheeger energy is like a norm in this Banach space to the power p composed with a linear operator. That's the only information, more or less, that we need to know. So this abstract machinery of contingent modules is giving us this formula. And now I will show you how to prove the inclusion between the spaces. So it's we are going to use a resulting convex analysis that we learned from paper by Bouchité, Buttazzo, and Seppecher. So we consider the differential conjugate of the Cheeger energy. I call it EP star. Then we look at the differential I was mentioning as an unbounded linear operator defined on LP. So one can show that this is densely defined, unbounded linear operator. So you can consider its adjoint. And then we consider the domain of this adjoint, so where this adjoint operator is actually defined. The resulting convex analysis tells us that the differential conjugate of the Cheeger energy can be expressed in this form. Right? So here you have the norm in the dual of the cotangent module to the power q. And the reason is that this is the differential conjugate of the norm to the power p. And then we are using here the linearity of the differential d. So we are taking the infimum among all L, elements L in the domain of the adjoint, such that this star of L is equal to the function g that we fixed. Okay. Now, to conclude, I need a couple of more information. So first one, Cheeger energy is convex lower semi-continuous, so it agrees with its second differential conjugate, its double differential conjugate. And second ingredient, as you might expect, every element in the domain of the joint induces a derivation with divergence in a natural manner. So if you take an element in here, it induces a BL, derivation with divergence, and the divergence corresponds to minus the adjoint applied to L. There is just this convention for the sign, but okay. So now, just to recap, we have this formula, this sort of min-max theorem, min-max result for the dual Cheeger energy. We have that EP is the same like its second dual, and we have this relation between domain of the adjoint of the differential and derivation with divergence. So now we combine all this together. So we start with a function f that is in W. So a priori, its Cheeger energy might be plus infinity a priori. The goal is to show that it's finite. So the Cheeger energy is the same like its second dual, and that you can write explicitly. Once you are here, you can apply all the results that I mentioned in the previous slide. You just do the computation, and you end up with this formula. So here you have the supremum over all derivation with divergence. And now, here you essentially apply just the definition of divergence, and you apply Young's inequality, and you can show that this supremum is smaller than the norm of dfw to the power p. Okay? So this tells you that the Cheeger energy is finite, but it also tells you that the norm of the minimal relaxed slope is smaller than the norm of the minimal Kappa gradient. Okay? So this is proving the other inclusion, and it is proving the integrated version of this inequality, but we have the pointwise inequality in the other sense, right? So we can still conclude. Okay, and so some comments about this inclusion. So first of all, it's a more general principle, as I was saying. So it covers also like finite or boundedly finite radon measures over arbitrary metric spaces. And actually, even more in general, it works even for extended metric topological measure spaces. That is one of the main results we obtain in this work in progress with Janne. But second comment, I think it doesn't work for p equal to 1. But what you can get in that case is an equivalence for BV spaces. This is what we're doing in a work in progress with Giacomo Sodini. Okay, so this was about H equal to W. I will just say something about N equal to B, so the approach with modulus and the approach with plans. I will not say much about it, but I just mention something. So this identification follows from the modulus plan duality. So this was originally proved by Ambrosio Di Marino and Savaret. So the key result is the following. So if you take a set of curves that is Susselin, some measurability assumption, such that the P modulus is positive and finite, then you can find a plan with Q body center for which you have this formula, right? So you have this duality between modulus and plans. So roughly speaking, it means that the negligible sets for the modulus is essentially the same like the negligible sets for like all the plans with body center together. Okay, so this was proved when P is bigger than 1. So the argument is more or less the following. So when gamma is a compact set of curves, you can prove it. And then you can use the fact that the P modulus for P bigger than 1 is a Choquet capacity, which in a sense means it's irregular. And then by approximation, you deduce it for every set of curves that is measurable in some sense. This argument is not going to work when P is equal to 1. And the reason is that the 1 modulus is not a Choquet capacity. And this was proved by Honslova, Exnerova, Kalenda, Mali, and Martiu in this paper. However, we can still prove something a bit weaker that is still enough to prove this identification. So what we did, we proved this formula, so this modulus plan duality, even for P equal to 1, when gamma is a compact set. We cannot deduce it for every other set, but still we showed that this is enough to prove the equivalence. So knowing this for compact set with some extra argument is enough to prove equivalence, N and B, even though we don't have the full duality formula in general. Okay, so this is what I wanted to tell you about N equal to B. Okay, now I would like to make another comment. So the first thing we have seen was the equivalence between H and W. So both these approaches are in a sense Eulerian. So they look at the behavior of functions, the involved function. And it's a kind of general duality principle. In this slide, we have seen N equal to B. So both these approaches are some kind of Lagrangian approaches. So they look at behavior on curves. And now we need to bridge the gap between the Eulerian and the Lagrangian worlds. Right? And I'm gonna do it now. And the key, I mean, to bridge this gap, the main result is the following. This is some kind of informal statement on the result. I will not give you full details, but this is a result that we proved in a second paper, a work in progress with Luigi, Tony, and Danka. So roughly, the result is the following. So you take, if you take a plan with Q body center, you can associate to that a Lipschitz derivation in a natural way. So just by integration, right? So by just superposing the action of these curves weighted with the measure pi, you can get a derivation. Okay, what we prove in the theorem is that you can make it into an identification in some sense. So the more difficult thing is the converse of this. So if you now take a derivation with divergence, can you find a plan that is representing that derivation? That's the more difficult task in a sense. And we can make it into an identification in some sense. So plans with Q body center will correspond to integrable Q derivation whose divergence is a finite measure. I would like to allow also for the case where divergence is a measure. Okay, and so what it means is that if you take now a derivation with divergence, that is a measure, you can find a plan representing it in an optimal way. So that the pointwise norm of the derivation corresponds exactly to the barycenter of the plan. So you might have different plans representing the same derivation, but here I'm interested in the optimal representation of the derivation. So I want to have this identity here. And the divergence corresponds to the what we can consider like the boundary, or actually minus the boundary of the plan pi. So EV is the evaluation map. So EV at time 0 means that you send every curve to its initial value. It's the same for at 1. Okay. So the divergence corresponds exactly to minus the boundary of the plan that is defined in this way. Okay, so this result is a consequence of the superposition principle for normal metric one currents that was obtained by Paulini and Stepanov in the metric setting. And this sort of strategy appeared previously in a paper with Simone Di Marino and Nicola Giglia and Eleftherios Soltanis that I presented actually at this conference 6 years ago. And 6 years ago, yeah. And so we started from those results, and then we actually proved this identification recently. And this strategy works also for p equal to 1. Okay, so once you know this, then you can show the equivalence between, all the approaches essentially. And but to conclude, I would like to present another result that is a bit weaker than this, but is still sufficient to prove the equivalence of Sobolev spaces. And I would like to present it because here it's very, it is illustrating in a very clear way how the optimal transport comes into the game in this case, right? So it's a weaker result, but actually it works in a more general setting. So it works even for the extended metric topological measure spaces that I was mentioning before. So the argument is more or less taken from paper by Giuseppe Savare. So here I'm assuming that the space is compact and length space. So this is an extremely strong assumption, but I would just like to give you some kind of proof of concept. So I will not try to remove this assumption, but I just mentioned that if you work in extended metric topological spaces, you can somehow always reduce to this case, right? So I will just give the proof in this very restricted setting, just to give you the ideas, the flavor of the proof. Okay, so what I would like to do, maybe I can first tell this. So I would like to start with a derivation with divergence, that is a measure. And I would like to find a plan that is associated to that in a way that is a bit weaker than the identification I was telling you before. So I take this derivation, divergence, I call mu the divergence for simplicity. And now, okay, I need to introduce some definitions, some concepts. So if you take a continuous function on the space X that is strictly positive, you can regard it as some sort of conformal metric density. So you can look at the length conformal distance induced by G. So you minimize the length of curves joining the 2 points when you take the path integral of G. So that plays the role of your metric. And once you have defined this conformal distance, you can define the associated Kantorovich-Rubinstein distance. Okay, so you take the optimal transport problem where you take this conformal distance as your cost function. I'm just interested in considering the distance between the positive and the negative part of the divergence, mu. Okay, so I look at all measure on the product whose push forward on the first variable is the negative part, on the second variable is the negative part. Okay, so I look at this Kantorovich-Rubinstein distance between positive and negative part. Okay, another ingredient we need is the so-called dual dynamic cost. So you consider this quantity, so you take the infimum of the norm of the barycenters to the power q, where you take all plans whose initial and final distribution are respectively the positive and the negative part of mu. Okay. So what is the relation between the dual dynamic cost and the Kantorovich-Rubinstein distance is the following. So if you apply the von Neumann-Minkmax theorem, you get the following. So the dual dynamic cost is the supremo of this functional, where here you have the Kantorovich-Rubinstein distance among all function G that are continuous metric densities. Okay. And now we need another ingredient. So we need this sort of dual formulation of the optimal transport problem. So we need to know that due to this specific choice of the cost function, you can show that this distance is the supremum of the integral of phi in the mu among all functions phi Lipschitz whose asymptotic slope is smaller than G. So this is due exactly to, our particular setting, our particular choice of the cost function. Okay, so, and now we are done. So now we just have to combine all these pieces of information. So now we have 2 variables. So we have the function G, that is the density, and then you have the function phi that satisfies this inequality. Okay, so you are basically taking the supremum among all g and phi in this class of this quantity. Okay. Now, okay, I've skipped all the computations, but you can trust me that if you apply all of what I've said so far, you end up proving the following. So you can prove that, again, by just definition and Young's inequality, these quantities are smaller than the norm of derivation to the power q divided by q. Okay. So by taking the supremum on the left-hand side, it means that q times the dual dynamic cost is smaller than the norm of the derivation to the power q. And now we can use, if you wish, the compactness, for example. So you can show that this infimum is in fact a minimum. So you can select a plan with body center for which you have equality here. And this, what does it mean? It means that this plan that you obtain, p pi of b, has the following properties. So the norm of the body center is smaller than the norm of the derivation. And the boundary of the plan is exactly minus the divergence. Okay, so this is a weaker form of identification duality than the one that we have seen before. But if you look now at the definition that we consider, this is still enough to conclude. Okay, and okay, I think, yeah, maybe we can stop here. Yeah, thank you.
Thank you very much, and there is some time for questions. Allora.
Other than the bridge theorem, the superposition principle, all the results you stated are for p greater than 1 or BV, right? So I mean, p equal 1 is is more difficult. So you need different techniques. So can you elaborate a little bit on the technical obstructions and on how maybe you overcome them?
So, for example, so the point is that L1 is not reflexive, okay, basically. So for example, if you look at, so okay, this means that the Chigger energy for p equal to 1, I mean, it's not really a lower semi-continuous envelope. So the lower semi-continuous envelope you get, it giving you BV. Okay? So, and this is visible, for example, yeah, here. So when you do this, when you take the second potential conjugate, this doesn't work. Okay. So what is the point? So basically, Sylvester, Ericsson, Biquet proved that H and N are the same, and via different argument, it's some sort of metric approximation in a sense. And then what we proved is that N is equal to B, thanks to this result. So this works even for p equal to 1.
Okay, and then the bridge.
And
yeah, okay, thank you. And also, if I may, another question. So in the classical case, there are like other spaces like Bezov, Tribel-Dizorkin, etc. So in the metric setting, is there something like, a generalization of these spaces, and are there some results which extend the classical inclusions, equalities, etc.?
Yeah, so I don't know much about it, but there are also other notions, like also Orlick's Sobolev spaces, or also fractional type Sobolev spaces in metric measure space setting. I would guess they're mostly studied when you are in a PI space, maybe. So when like you have some extra assumption, like doubling and Poincaré. But yeah, I don't know much about it. Yeah.
Thank you.
Okay, so we are perfectly in time to start. It's a pleasure to introduce Professor Shinichi Ota from Osaka University. He will talk about the generalization of Grunbaum's inequality in RCD 0n spaces. Thank you. Okay, you have already the microphone.
Yeah. Thank you for the introduction, and I thank the organizers for this opportunity. I'm very happy to be here again. And my talk will be in about Grunbaum's inequality. So this is very fundamental inequality and very simple inequality in convex geometry. And we consider a version in curved spaces, more precisely RCD 0n space. Okay. And okay, yes. Okay, let me start with the Grunbaum's inequality in the classical setting of in Euclidean spaces. So it's in 60s, but in paper by Grunbaum. So we consider a bounded convex set in the Euclidean space. Maybe, I don't know, like this. Then we consider average on this set, more precisely the barycenter over centroid of this convex set. I don't know, maybe so. Then for any half space whose boundary passing through this X node. So we consider, yeah, we cut this convex set in any way passing through this point, and we consider the intersection of this half space and the convex set omega. And then Grunbaum's inequality that we have a lower bound of the volume of this set. I mean, this is half space H. This convex set is omega. Okay. Like this. Okay. Like this. Okay. Okay, then, so this is a sharp estimate. Actually, do you have equality for cones? And what is important here is that this constant can be bounded below. I mean, we have dimension-free estimate like this. I mean, so this one is bounded from below by e to the -1 for any n. So this is very fundamental inequality. And from statistical viewpoint, this estimate means that this x naught is a deep point. So I mean, yeah, this inequality gives a notion called the root case depth in statistics. So this x naught is the deep point in statistical viewpoint. Okay, so this is very fundamental inequality and Grunbaum's by Grunbaum. And here we consider convex set, and it's in the average point on this convex set. And as I said, this x naught can be regarded as a barycenter. More precisely, it's a barycenter of the uniform distribution of this convex set. And instead of uniform distribution, we can also consider probability measure. And actually, if for the moment condition, we consider just finite first moment. I mean, we consider probability measure of finite first moment. Then we can define the barycenter of this probability measure as minimizer of this kind of function. Here, we consider distance distance from some point, square distance integrated by this uniform probability measure. And if this probability measure is of finite second moment, we just need this first term. But for probability measures which has only finite first moment, we add these terms and this integral is finite. And then if we consider the minimization problem, this term is not influential. So this first term is only the problem. Then we can define the minimizer of this kind of function, the barycenter. Okay, so in this way, we can also consider probability measure. And in this case, we have a generalization by robust Bempara. Yeah, this inequality may be known before then, but I couldn't find any literature about it. Okay. And here, instead of the convexity of the set, we assume the log concavity of the probability measure. But I think it's It's very common in convex geometry. Then, for the concave probability measure of finite first moment and its barycenter node, we have similar inequality, and we have the same estimate as the dimension free bound in Grunbaum's inequality. Okay, so this is the probability measure version of Grunbaum's inequality. And there are some other generalizations or related to inequalities. And for example, when we consider just general probability measure instead of log concave one, then we can still find some point x node, which satisfies a similar lower bound, but of course with a worse constant, 1 over n plus 1. Yeah, in this case, we just consider any probability measure, not necessarily log concave, but then so this x0 may not be barycenter, but we can find some point satisfying this kind of inequality. So this is also by Grunbaum in the same paper. And actually the proof is by using Helly's theorem. Okay, and then the point is that this estimate is not good if in a very high dimension, since this 1 over n plus 1 goes to 0 when n goes to infinity. So we don't know, we don't have dimension free bound. Okay. Then, so far we consider only Euclidean space, and it is also natural to consider what happens when we consider curved space. And there's one known result in Adamant space, Adamant manifold. Okay, so this is by Luciano in 2020. And actually, this is a generalization of the latter theorem. So, sorry, this one. And okay, so here we consider Adamant manifold and dimensional Adamant manifold. Adamant manifold is a simply connected, complete Riemann manifold of non-positive sectional curvature. So, like hyperbolic space. Then, for any bounded convex set of omega, we find some point x naught, and we have similar inequality to the result to Grunbaum's inequality, Grunbaum's second inequality. And here, of course, in this kind of curved setting, the meaning of half space is not clear. So in this result, we consider half space like this. Okay. Yeah, so half space is defined like this. So we fix some point, we begin with some point x, and then we fix some tangent vector v, and we consider a geometry emanating from this point x with angle less than pi 2. Yeah. And we consider these geometrics, and we have a kind of half space. Yeah. Yeah. So since the Adamant space is diffeomorphic to the Euclidean space, I think this is one reasonable way to consider half space in the curved case. Then we have this inequality. So this is nice, I think, but in the same paper, it has also shown that we cannot improve this estimate, even we consider convex set. So we don't have dimension-free estimate, like Grunbaum's first inequality. The definition is like this, but here we consider half space with this. The generally half space is defined like this. Yeah. Okay. Okay, so we don't have the dimension rebound. Then, so instead of other manifold of non-positive curvature, in this talk we consider negative curvature. And then, so this is corollary of our result. So, yeah, so this is joint work with Victor Brunner and Jordan Sellers. We consider LCD0 in space. So I will just briefly explain about this. This is a metric measure space with rich curvature bounded from below. And in this case, no negative rich curvature for positive and finite n. Then for convex set with finite on positive measure, and for any Weyl center of the uniform distribution on this convex set, and for any straight line, the associated Boltzmann function satisfies this inequality. So this is very similar to Grunbaum's first inequality. Okay, and I will explain about the Boltzmann function. And here, since we assume the existence of straight line, we can use splitting theorem by Nicola. And then, so this Boltzmann function, this sublevel set of Boltzmann function is something like half space. And actually, in some literature, this kind of set is called horoballs. Yeah, here we are employ horoballs as half spaces in this setting. Yeah, for RCD setting. Okay. Then we have nice estimate like this. Okay, so this is actually a corollary of our results. So we more precisely consider case of for probability measures on RCD0 space. And here are some other comments. So here we consider a convex set, and we didn't assume boundedness, but actually it is for free. So if we consider convex set with finite volume in RCD0 space, this is also necessarily bounded. So we don't need to assume it. Okay, I mean, CD0 plus finite volume implies boundedness. Yeah, so this is just by Bishop-Gromov estimate. And in this generality, Weyl centers are not unique. So we just take any Weyl center. Since we consider non-negative curvature, in this case, we cannot expect a uniqueness. I mean, in non-positive curvature case, Weyl centers can be unique, but in non-negatively curved case, we don't have uniqueness. Okay, and as I said, we can also consider probability measures on RCD0 space. So this is in the same spirit as Robert Spenpar's result about log concave measures on Euclidean space. Okay, and about the proof, let me just briefly comment. So as I said, the main ingredient is splitting theorem, and also to consider rigidity. I mean, when equality holds, we have some partial result in this direction by using the localization method by Fabio and Andrea. Right. Cones. Yeah, cones, yes. Yeah. Okay, so this is, and actually the proof is very simple, and yeah, very simple if we use splitting theorem. So it will not take much time. So I here also comment on the connection with convex geometry. No, convex optimization. So this Grunbaum's inequality has some applications in convex optimization. Yeah. So okay. So in what kind of convex optimization? Here we consider a convex function on a convex set in a Euclidean setting. So some convex set, and we consider convex function on this convex set. And we assume that function f is bounded below, and say we know roughly the minimum of this function, and we want to find a point which is close to minimize of this function f. And more precisely, you consider a sub-level set of this function f. For some c, this c may be sufficiently close to the minimum of f. Okay, minimum of f. Then, since f is convex, so this k is also convex set in this omega. So omega is the domain, and we consider some convex set k, sub-level set. So we want to find some point in this k. Then, so the algorithm is somehow related to so-called separation oracle or cutting plane oracle. So this gives us for a given point x. First, it tells that if this point is k or not. It's k is in k or not. And in this case, we just consider the value of f at this point, and if this is bigger than or less than c, so we can check it. Okay. And if it's in k, so it's okay. And if your point is not in k, I mean, like this, then this oracle gives us a hyperplane passing through this x. And also tell me on which half space k is included. And in this case of complex functions, we can use the gradient or subgradient of f at x to find on which part k is included. Okay. So I think it's a natural procedure. Okay, then we begin with the barycenter of this omega. Then if by the separation oracle, if this x naught is already in k, it is okay. There's nothing to do. And if not, we have half space h like this. Okay, maybe on this side, I don't know. Okay, I mean, yeah, half space including k. Then, so since k is on this side, we don't need this part. Okay, so we remove this part. And then Grunbaum's inequality is that this part has sufficiently large volume. Yeah, we have the dimensionally bound. Okay, so even for high dimensions. Okay, then we replace omega with this remaining part. Yeah, remaining part. And then we consider a barycenter of this part. And then we iterate. Okay. So this is the algorithm using Grunbaum's inequality. And this algorithm seems nice from geometric viewpoint, actually, and also effective from the theoretical viewpoint. But I'm not familiar with the implementation. I heard that computing barycenter is usually very expensive. So in this sense, in practice, it may not be very useful. But at least from theoretical viewpoint, this looks very nice algorithm. Okay. So this is how to use Grunbaum's inequality in convex optimization. Okay, then I switch to the RCD setting, and I will explain how to prove our version of Grunbaum's inequality. Okay. Then, so if you know convex geometry, Grunbaum's inequality is known as essentially the one-dimensional inequality, So we can reduce to the one-dimensional case in some way. So it is natural to start with the one-dimensional case. And yeah, we consider a one-dimensional, so CD0n space. And CD0n means that n-dimensional rich curvature is non-negative. So 0 is for non-negative curvature, and n is for the choice of rich curvature. And in the context of convex geometry, this CD0n just means that 1 over n concavity in the sense of Borel. Yeah, so in this sense, this CD0n is a generalization of convex geometry to curved spaces. Okay. Okay, so we consider one-dimensional space. So just the interval with usual Euclidean distance and measure with density function W. Yeah, and in the Bandy Grunbaum inequality, we assume that this measure is probability, so integral is 1. And also the 0 is the bar center. I mean, just by translation, we assume that the 0 is the bar center of this measure. So this means that 0 is the bar center. And then the CD0n condition is just the W to the power 1 over n minus 5 is concave. So there is just 1 over n concavity in the sense of Borel. Yeah, we assume this concavity as a CD0n condition. Then we have this Grunbaum inequality. So since 0 is the bar center, this is really the half space. I mean, 0 is bar center, so this is half space. Then we have this Grunbaum inequality. And so this inequality is very simple and actually easy to show. First, by assumption, I mean the concavity and probability and so on, we can easily see that the interval is finite. Then we consider cumulative distribution function, so capital R. And then by integrating the concavity condition on the density function, we can show that this cumulative distribution function is also concave. I mean, to the power 1 over n is concave. Yeah. And this is really straightforward from Borel-Blanchkamp-Lieb inequality, or more precisely, which we can just use Helder inequality in a correct way, then we have this concavity. Then together with the boundary condition, so since capital R is defined like this, it's 0 at A and 1 at B. And by combining this boundary condition and the concavity, we have this inequality. So this is very simple. Yeah. And since the proof is very simple, we can also consider the equality case. So we have equality here, only for columns, as I said. Yeah, here for 2, 3, and this coefficient is just for normalization, since W is probability density, so it's just for normalization, and the function is really like cone. Yeah, so this density vanishes at A, and it's like cone between A and B, or order n minus 1. So okay, this is the one-dimensional case. Okay, and how to use this to show the general case? Okay, so in general case, as I said, we consider our CD0n space. And our CD means that this R is from Riemannian, and CD is just CD0n. Okay, and I don't really give a definition of this space. But if you don't know this space, you can just consider Euclidean space with 1 over n concave measure. So yeah. Then, so in this context of actually n space, if we assume the existence of straight line, this is a globally minimizing geodesic or constant speed. Okay, we consider existence of straight line. Line gamma in our space X, and then we can define Boltzmann function associated with this gamma. So we, for some point X, we consider T minus distance between X and gamma T. So gamma T is somewhere here, and maybe somewhere gamma 0. And this means that T is the distance between gamma 0 and the gamma T. Okay, so this is T, and minus distance between X and gamma T. Okay, so we consider the difference of these. And if T goes to infinity, then it's like this. Then the difference is somehow this difference. And this is the Boltzmann function. Okay. Yeah, so in this case, Boltzmann function is the negative, I think, and no positive. Okay. In this case, positive. If X is somewhere here, then it become Boltzmann function is negative. And then, so just by definition, it's easily seen that Boltzmann function is one Lipschitz. I mean, this limit exists, and Boltzmann function is one Lipschitz. And also, not as in the picture, it can be regarded as a projection to the straight line. Okay. Then, by using this kind of Boltzmann function, we can show kind of splitting theorem. Splitting theorem means that we have splitting structure. So real line times the space of codimension 1. Okay, and this goes back to Chiga-Gromor's very influential result in 70s in the Riemann case, and this was generalized by Nicola in an RCD setting. So when we have straight line, then we have this kind of isometric splitting. So our space, RC0 in space, is isometric to the real line times some metric measure space. And this metric measure space is again RCD0 n minus 1, or just a singleton if in a very low dimensional case. Okay, so this means that roughly, so if our space is non-negatively curved, so the space cannot diverge like the hyperbolic case. The space can be contract, but cannot diverge like hyperbolic space. But since we have a straight line, we cannot contract. Yeah, I mean, then so we cannot contract, but we cannot diverge. So it is straight line. We have splitting structure. Yeah. Okay. And actually, this Boltzmann function is actually the projection to this one dimension space. Okay. Okay. Then by using this structure, we can now it's not difficult to show Grombaum inequality, and here I state the main result. Yeah, for probability measures on RC0 in space. So we consider metric measure space, so which is RC0n, and we consider probability measure on this space. And as in the robust membrane result, we need to assume some concavity of this density function. And here we consider this density function rho satisfies this concavity. So rho to the power 1 over beta minus n is concave for some beta bigger than n. Then for any bar center of this property measure and for any straight line, we have this inequality. So the volume of the hollow ball is bounded like this. Here we have similar estimate to the Grunbaum's inequality, but for this bed. Okay, so this is our Grunbaum's inequality in the general case. And if we really want to recover the previous corollary I mentioned for convex sets, we just consider uniform distribution on a convex set and let beta go to n, then we have corollary for the convex set. So, okay. Okay, then how to show this via the one-dimensional analysis? And so this lemma is really the key step. This is simple, but really the key step. Okay, first, by translating the straight line, we can assume that the Boltzmann function at the bar center x naught is 0. This is just by translation of the straight line. Then we can show that the integral of the Boltzmann function is 0. And how to show this? We consider a straight line passing through the bar center x0. Oh, maybe I use this one. Oh. Yeah, we consider straight line passing through x0, asymptotic to gamma. And in the product structure, we can just write down this straight line like this. It is just it. Okay. Then since x0 is the bar center, this function has takes minimum as t is 0. I mean, this is the integral of the square distance from eta of t, integrated by this measure mu. And since x0 is the bar center, this at t is 0, it takes minimum, so we differentiate it should be 0. Then, so this distance, yeah, we consider distance from eta t to some x. Okay, maybe x naught, but some x. Okay, it's not good here. Some x. And we consider distance like this. But from the product structure, this distance is decomposed like this. I mean, scalar distance of this here, and sum of square of this distance, sum of square of this distance. But this distance is independent of t. You know, only this distance depends on t. And this is actually the this distance. Okay. And then we differentiate at t is 0. Then we have this integral of the Boltzmann function, and so it should be 0. Okay. And so this is very simple. And this means that if we project our probability measure to the real line, then by the Boltzmann function, then 0 is the bar center. So we consider push forward of our probability measure by the Boltzmann function. And we do not the distance density function by W. And we can first show that this density function satisfies some concavity. So this is very similar to the proof by the Borel-Brush-Camp-Lieber inequality. So I explained in the one-dimensional case. It's very similar. And in that RCD setting, we have Borel-Brush-Camp-Lieber inequality by Kathleen Braha. and we can use it to show the concavity of the density function. Okay. Then, so this one-dimensional distribution satisfies concavity. So, and then, yeah. So this one-dimensional space is CD0 beta space, and the previous lemma, so key lemma, means that 0 is the bar center of this density, this probability measure. Then we can apply the Grunbaum inequality in the one-dimensional case. Yeah, so we are done. Okay, so this is good enough to show the inequality itself. We can reduce it 1D case by pushing forward by the Boson function. Yeah, so this is good. But if we consider also the equality case, I mean the rigidity problem, so this is not good enough. So we also consider any alternative proof by using localization or needle decomposition. So this proof gives more precise information. And so this is again by key lemma. So the integral of the Boson function to the probability measure is 0. And so this probability measure has density rho. So we actually have this equation. And then by using this, we can build the localization. Okay, and about localization, I just briefly explain. So this is again very nice application of the optimal transport theory, L1 optimal transport theory. So we obtain a decomposition of our metric measure space to one-dimensional spaces. Yeah, so we have decomposition xq, and also a measure on this space of on this space. And here xq is the measure of minimal geometric and also called the needle. And each needle has a property measure mq. And then with this property measure, this needle is a one-dimensional CD0n space. Yeah, so we can reduce the problem to this needle, since this needle has again the same curvature condition. Okay, and also this condition still holds for almost every needle. Okay, and also this measure is indeed a decomposition of the original measure in this sense. Yeah, so I have just a rough picture like this. So yeah, we have a straight line, and our measure, okay, since the integral of the Boson function is 0, so our property measure has support on the positive part and negative part of the Boson function. And the needle decomposition is constructed as L1 optimal transport from the negative part to the positive part of the Boson function. And it's something like this. Okay, so we have decomposition in the geodesics, and L1 transport is done along those geodesics. And these geodesics have satisfied the same curvature bound, CD0n. So and also we still have this equation on almost every needle. Then we can apply the 1D analysis to those needles. So okay, we now put density function for the original property measure mu on needle, and since this is again CD0 beta space, we have 1D Grunbaum's inequality on almost every needle, and we integrate it to have the global Grunbaum inequality. Okay. Then this gives more precise information. Since the previous proof, we push forward everything to the one-dimensional case. Then we don't have a very good information about in the equality case. And here we have the information along all needles. I mean, almost 7 needles. Okay. Then by using this proof, we can at least show that if equality holds in our Grunbaum's inequality, then equality holds for almost every needle. Then by the analysis of the equality case in the 1D CD space, every needle, almost every needle has cone structure. So this is seen in our proof. Yeah. And also, I didn't say about this, but we also have versions for other parameters. So beta can be infinity or negative, or maybe 10 also can be infinity or negative. In this case, we can also show appropriate versions of Grunbaum's inequality. But maybe one remark is that for n infinite or negative, we don't have splitting and localization in the RCD context. We have splitting and localization or only in the smooth context, weighted Riemannian case. Yes, so weighted Riemann manifold, we have splitting by Fan Li, Zhang, and Wiley, and also localization by the original work by Kratak. So by using this, we can also consider those cases in the smooth setting. Okay. Okay, then about the rigidity. So I think this is the rigidity only along needles. And about the structure of the measure mu itself is a different story. I mean, yeah, we know that almost all needles are nice construction, but we don't know how the configuration of needles. They don't intersect, but this may be something like something like this, and we don't know. It's not good. And what we expect is really the cone. Yeah, and it's still open. I mean, yeah, yes, we expect that at least on our Riemannian manifold, and if equality holds in our Grunbaum's inequality, then yeah, we are essentially in the non-collapsing case, and the support is convex cone. We expect this, but it's still open. Okay. And actually, the rigidity is at far side, rigidity is known only in the very classical unweighted Euclidean case. And in this case, even the stability is known by Groma in 2000. I mean, the reverse inequality without this epsilon is the Grunbaum's inequality. So this is the reverse Grunbaum's inequality with the deficit epsilon. Okay. In this case, we can say that this omega is close to a cone, like this. So the omega includes a cone k, and the difference is small in this sense. Yeah, depending on the deficit epsilon. Yeah, so this is nice stability result. But this kind of stability is not only in this very fundamental setting, and other cases we don't know even rigidity. Yeah, so this is open problem, and also I expect some connection with convex optimization, but our result depends on straight lines. It's very beautiful, but not useful. So I don't know how to apply. Yes. So if you have some ideas, I'm happy to discuss about it. Okay. So thank you for your attention.
Thank you very much. And we have some time for questions. Yeah.
Just a quick question / comment. It seems to me that you don't really need the RCD and the splitting. Would the same work if you start from a CD 0 and space times a real line? Yes, suppose that you have a split that splits for whatever reason, not because it's RCD, but just because it's the product of a line and something. The proof would go through. I mean, do you need any other tool from RCD theory, like, I don't know, Sobole's functions, Hilbert? You see what I mean, right? I mean, because the picture that you draw seems only to rely on. No?
Yeah, actually
even the rigidity case, I mean, with the localization.
Yeah, so this key lemma is
exactly.
somehow we have really the derivative product structure here. This is 1 point.
Okay.
I mean,
but if you know that the distance has, at the structure, maybe it does, right? I don't know. Just
proof is actually very simple, so we may consider some difference.
Okay, thank you.
More questions, comments? Okay, I don't see. So let's thank you again, Professor Ota, and for a short break. Okay, so we can continue with the talk by Lorenzo Portinale from Bonn University. He will talk about nonlinear minimum cost flow problems in a random environment. Thank you.
So thank you very much a lot for the invitation. It's always a great pleasure to be back in Pisa. I spent some of my years here together with Professor Ambrosio, and it's always very nice to be back. So thank you very much. So today I'm going to talk about joint work. I should say in progress. The hope is actually that this paper will be out on preprint this week. So we're kind of like very tight on time. And together with Peter Gladbach and Yamas. I'm going to talk about nonlinear minimum cost flow problems on graphs in a random environment. So the plan of the talk is essentially to discuss a little bit the classical nonlinear minimum cost flow problems, discuss about the random environment that we want to consider. So what do we actually mean with random environment in this setting? And then I'm going to discuss a little bit about how to take scaling limits, meaning describing this kind of mean flow problems on very large random graph, and try to understand if we can describe the effective behavior by taking into account the limit as the graph is approximating the continuous setting. I'm going to give a few ideas about the proof, not much, just the key points somehow, the major contributions to actually prove this result. Okay, so let me start from the general setting. So the general setting we have in mind is the following. So we have an undirected connected graph. So X and E are simply like a bunch of vertices and edges, like in this picture. And what does it mean to discuss minimum cost flow problems? Meaning we're interested in looking into scalar flows at this level. I'm going to talk about how we actually generalize this. What is a scalar flow? Well, simply it's a function from the space of edges into R. So for every edge, let's say, for example, this green line here, we take an antisymmetric function, which means simply that the flow of mass along one edge is minus the flow in the opposite direction. So it's an undirected graph. And for each edge, let's say for each of this green line, we assign a cost function, which I denote by Fe. So in each edge, we assign a cost, which you can interpret in the following way. So if I take a flux J, a number in R, Fe of J is really the cost of flowing J units of mass through the specific edge. Okay, so different edge can have different type of costs. And for each of the edge, I assign a different type of cost. Okay, and what we have is like we have a cost function on the space of on the edges, and then we have essentially a prescribed net flux. Yeah, so a measure which is sum equal to 0, so a sign measure of mass 0, which essentially is describing in each vertex how much supply and demand I actually have at the specific edge. Okay, you can imagine that you have flows from different edges around one single vertex. And for example, if I say that m is equal to 0, I'm assigning essentially divergence 0 condition on my flux, which means that the sum of all the contribution must be 0. And this is somehow given from the problem. Okay, so we're going to see actually later when they talk about the continuous level, this is nothing but a different way to formulate, for example, Wasserstein 1 distances as well. Okay, so that's also how it's related to optimal transport. Okay, so what I want to do, I want to discuss minimum cost flow problems. What does it mean? This comes back from very, very long ago by Ford and Fulkerson. I want to minimize the total cost, meaning I take a function, a flux J, I take the sum over all the edges of my cost along each edge assigned to the specific flux that I'm choosing, and I minimize over all the possible fluxes, I minimize the one that are prescribed divergence. Yeah, they have exactly the net flux that I'm imposing. So this condition essentially means that the discrete divergence of my flux is equal to the assigned mass m that I have on my problem. Okay, this is a discrete version of essentially a time-independent continuity equation that you usually have when you work on optimal transport. If you go in the classical Benamou-Brené formula, for example, you reduce the case to p equal 1, the problem becomes time-independent, and the continuity equation really becomes essentially, like Enrico was also discussing before, divergence equal to the sources, the difference of the sources. And that's exactly the same at the discrete level. Okay, so we want to study this problem. As I said here, typically the problem is set in dimension 1 in R. So this is one of the most important examples we have in mind that we should always keep in mind, which is exactly this less than 1 kind of formulation where the cost of flowing along each edge is really proportional to the flux. Okay, so if I fix some weight along the single edge, I get exactly something like this. And in this case, also at the discrete level, this is really a vastest than 1 type distance in the sense that if I now consider a suitable distance which is induced by these weights on the graph. So for those who maybe knows a little bit about graph theory, if I have weights on the edges, I can define a distance on the graph by simply taking all the possible paths. I count the weights along the path, and then I minimize between all the possible choices of the path. Okay? And if I use this distance, I can define as in usual sense the vast than 1 distance between probability measures or measures with the same mass in general. And this actually is exactly the same as the problem I just posed before, which is essentially a discrete version of the equivalence between the coupling formulation and the Benamou-Brené formula, for example, for p equal 1. Okay? So this is like a very special case. The fact that this equivalence is known by different ways, I put just a reference here by a work I did with Filippo Quattrocchi, which is also in the audience, where you can also find a nice clean proof of this equivalence in the graph setting. Okay, so what we want to do is to study these type of problems on a slightly more general level, meaning we're interested in 2 features, which makes our life a little bit more complicated, which is multi-species. So in particular now, think about the fact I'm flowing along the graph, but I don't have essentially one type of particles flowing. I might also have different type of particles. So my flux is actually something which is vector valued in this setting. So in each edge, my J describing the flow of n particles, for example. Okay? And the second thing is that I don't want to assume any type of linearity, structure, or convexity. Yeah? In particular, convexity, we're going to see by the end of the talk, it is a feature that creates some additional structure in the problem, which is non-trivial, and I would like to discuss. Okay, so my function f is not necessarily, for sure, it's not necessarily homogeneous, but it could also be something which is non-convex. And while looking around the literature, actually, before this talk, I found in some optimization book also some nice example of something which is very basic example of non-convex function, which is what they call in literature the fixed charge function, where essentially you don't pay if you don't move, but as soon as you move, you have like a cost of activation. Yeah, so this alpha E is an activation cost for which the moment you actually move, you are forced to pay a little bit already by the simple fact that you actually move, which creates a jump in this function, which already brings you away from the convex case. That's a very simple example here, but really somehow skip away from the convex setting. Okay, and then one thing I wanted to mention, which I'm not going to discuss in this talk, we don't actually have to cover only this type of energy, which is a sum of energy over the edges. It's just for describing the problem is much easier. We actually have a general cost function with some properties, but I'm not going to say more about this. But what I want to discuss a little bit about is what do we mean with random setting? Okay, so as I describe this problem is just about minimizing flows on a graph. My setting is fixed. In this setting, I have my cost functions. The problem I want to understand is, okay, what happens if I try to study this problem where I have a very large random graph, and maybe even my cost function could be random. And a typical setting, for example, coming from particle system is what we call like random walk in a random environment, which means that my environment itself is not fixed, but it can be realized in a random way, possibly stationary. And I want to understand what maybe in average or for every validation my problem really looks like. Okay, so let me give you an idea about what do I mean actually with random setting in this picture. We work with stationary random graph. Okay, stationary essentially means that I have no assumption of periodicity on my graph. But of course, if I don't assume anything at the level of the graph, the problem becomes extremely complicated. And typically, when you want to study scaling limits of transport problems on graphs, the periodicity assumption is replaced in the random setting what is called stationarity. Stationarity means that my graph can be extremely complicated, but essentially if I take my graph, which is now a random variable, so for every realization I have one possible graph, if I look at how is the law of my graph when I shift it by an integer, okay, if I shift it by an element in ZD, I don't get exactly the same graph, so my graph is not periodic, but essentially the probability of finding my graph in the original position or in the shifted position is exactly the same. Meaning that the law of the graph which is shifted is the same as the law of the original graph in a very intuitive way. And you can make it very rigorous, of course, by introducing suitable tools. Okay. As I said, so we don't assume periodicity on the setting, and of course, periodic graphs are a very special, non-really determined random setting. So in the sense that if I take, like I will tell you in a second, one example could be if I take a periodic graph and I simply use this as a deterministic object. Okay. So what we want to do, we want to consider stationary random graph, and then we want to have some geometric assumption to be able to handle the problem when we take the scaling limits. And the assumptions are the followings. So we have some geometric assumption on the graph, okay, that I want to discuss with you here. So there are essentially three assumptions. The first one is called the absence of large gaps. So we assume essentially that almost surely there exists a radius R for which if I now look around any point in my space, not on the graph, in any point of my space, if I look at a ball of radius R1 and I look around how many points of my graph I have inside this ball, I need to have at least 1 point. Yeah, because if large gaps would mean that I actually have a very large ball where I don't see any points, and this will actually create big holes that intuitively concerning transportation problems could actually create very, very non-trivial problems. The second one is quantitative connectedness, meaning my graph can be very different from the classical, say, periodic setting or RD. So when I try to go from one point to the other one, I can have to do very large detours. So what I'm assuming is that for every point, I can find a path for which actually the Euclidean length of this path is controlled by the classical Euclidean distance plus maybe one unitary term. And the third condition is bounded edge length, meaning, okay, I'm assuming, I'm allowing myself to have like not necessarily like one length edges, but I want to be sure that I don't have arbitrarily long edges, because this will actually create a non-local problem in the limit. Okay, so these are somehow assumptions which I need to have almost surely, meaning I have a random graph. I don't need to have this uniformly in my randomness. I just want to assure that whenever I look at my realization of the graph, there exists constants which depends on the realization for which I have these properties. Okay? Okay, so example about random graph, as I said, the simplest one are deterministic pictures which are periodic, which are not really random, of course, but I just wanted to discuss. For example, the symmetric grid could be a perfect example of a stationary, not really random graph. You can also make it a bit more non-symmetric in the sense you just fix a periodic graph like this, where essentially you copy-paste in each cube different locally finite graph. And this, of course, gives rise to some stationary setting, which is not stationary, it's really like purely periodic setting. But you can also make different examples. So for example, one that I also like is called random chessboard. I took this picture from Dalmaso Modica paper back from, I think, the 60s even, where essentially you take the symmetric grid and now you kind of deform the size of the grid by random variable. Yeah, you can take ID random variable, you decide that instead of doing the cubes, you just make it thinner or longer in a very independent and identically distributed way. This will give rise to something which is now with the nearest neighbor, is something which is not really periodic, okay? But of course, because you do it IID, you get something which is stationary because there's no difference about finding a certain graph or the shifted version of the graph. And another example that I wanted to discuss here, which I also like, are essentially Voronoi tessellations when my points are taken from a point process, which is also stationary. Yeah? So the picture I have in mind is the following. Say I want to describe first how the points are taken. So I have what is called the stationary point process, which is simply an amount of points in RD which are randomly distributed in a stationary way. So again, if I shift, I get essentially the same law. And I also assume, of course, that my point process has the same properties that I am assuming in my problem, so I don't want to have large holes. And I also want that my points are not collapsing too close to each other. Okay, this is the second condition here. And then I can do Voronoi. Voronoi tessellation means, well, I'm simply taking my points and I'm dividing my space into cells that contains the point. And how you define the cell? Well, the cell associated to a point X are all the points in RD which has X as the closest of the points that I have on my point process. So like in this picture, this cell is exactly all the points where this point is the closest with respect to the other one of my point process. And of course, the graph structure I'm going to use is the nearest neighbor structure. So if 2 points has phonoid cells which share an interface, then I'm going to connect them with an edge. Okay, so if you want to write it explicitly in formula, it's exactly this, but in practice it simply means if 2 cells are adjacent and they share an interface, I declare it to be an edge. Okay, and this you can show that they satisfy all the properties I was discussing before. Okay. Okay, so this is about essentially the settings on the environment, right? And then I want to tell you also what I want to assume on my energy, on my cost functions, which, by the way, as I said, I would like to be able to allow these energy functions also to be random, because as I have in mind, I would like to do, for example, I don't know, faster than one type of transportation where my weights are also random variable, okay? So my energy itself would be a stationary object, meaning for each realization of the environment, not only the graph is changing, but the energy itself could depend on the realization, yeah? So it's a random variable, so for each omega in the space of probability, I take a function, which is a cost function on each edge, and I assume this also to be stationary in the sense that the law of this function doesn't change when I shift the space properly. Okay, and the setting I want to describe today is the setting of linear growth structures, meaning the same sense of vastest and one kind of distances, where I have the dependence on the flux has linear growth in the sense that has the power p equal 1, so to speak, in the choice of the energy. This somehow goes back and forth from being a good assumption or a bad assumption, in the sense that on one side, linear growth, there's some control on the actual growth, but on the other setting, as we probably all know, when I work with linear growth functions in calculus of variation, typically this creates extra singularities in the limit, yeah? Because as in vastest 1, when I minimize the flux, the total variation of the flux, because I have linear growth, is not anymore like in the vastest 2 case, where essentially I cannot teletransport the mass. I have to have some sort of continuity. I cannot create irregularity in time. When I have linear growth, I will see singularities in my problem. So there will be fluxes which have finite energy, for which they're actually not absolutely continuous with respect to the time variable. Okay, so this is like an assumption that sometimes will create additional difficulties. Somehow, the final goal that we have is to go beyond this assumption, but we thought that this was actually the hardest one. Surprisingly enough, for now, this is the only set that we can actually cover. So the actual quadratic case, for example, is something that creates for us a little bit more problem, despite the fact that the singularities do not appear in the setting, for example. Okay, and the second condition I want to assume is Lipschitz continuity, which actually go back and forth from this linear growth assumption. Yes? No, they can depend on omega. Yeah, thank you. So essentially, because our result is essentially like a quenched type of results, meaning almost surely we're going to have a certain result. So what I actually need, the proof is mostly deterministic. The randomness will come into play as in the classical ergodic theory, essentially to ensure that certain limit exists, but the result itself is actually more deterministic in nature. Yeah. So this constant can depend on the omega. And then the problem is exactly the same as before, with the fact that now my energy is randomly dependent on this little omega and my graph itself as well. Okay, so exactly the same problem. Okay, so on purpose, just to either complicate or confuse you, or to actually go along with the question by Filippo, I will omit the dependence on omega, because our result is actually not really random in the sense that the proof is more deterministic in nature. The randomness only comes into play in the existence of certain limits. Yeah, I will comment on this. Ergodic theorem typically says that if you have certain stationarity properties at the level of the energy, then when you take certain limits, those limits exist almost surely because of stationarity, but the proof that you actually then do to prove the scaling limits results, they are actually more deterministic in nature. Okay? Okay, so what do we want to do? We want to study scaling limits of this problem, meaning I want to take my graph and my cost function, I want to rescale it, and I want to try to understand when epsilon goes to 0, if I multiply my graph by epsilon, for example, I take my random realization, I multiply by epsilon. If I look at a big box, my graph is getting denser and denser, and this graph is approximating my continuous space. And the question is, can I actually describe the behavior of the minima and the minimizer of this problem by some sort of effective behavior at the continuous level? Now, also because in practice, if I'm interested in the model that describe this problem on a very large graph, in practice, it's very hard to compute anything when the points are really lot and big. So in practice, we would like to understand if we can give give like a effective limit behavior of this problem. How do we rescale the cost? So the cost is rescaled in the following way. On purpose, I kept this notation originally, the notation of the original energy, and also wrote explicitly what do I mean, because it actually reflects exactly a typical behavior of the discrete problem for those who worked in these settings. For example, if I want to go from discrete to continuum, typically if I have an a sum, I would like to rescale problems by multiplying by some volume factor, right? So like in the same way as when I do Riemann sums, I want to approximate Lebesgue integrals, but the flux will rescale with a different factor. Okay, so the flux would actually rescale with a epsilon to the d minus 1, and this is essentially due to the fact that I'm not rescaling the divergence for real. I'm keeping the same discrete problem, and because I'm not rescaling the divergence by dividing by epsilon, which would be like a natural thing to do, I have a missing length scale inside the flux. Yeah? If you think about the fact that this is a good approximation of the divergence, well, this is a good approximation of the divergence if I actually rescale by the distance between the points. I'm not rescaling these factors, which means that I'm actually rescaling inside. Okay? Okay, the question is what happens when I actually go to 0, meaning let's say that I have my prescribed net flux is converging in some sense to some measure mu. This could be, for example, in the Waston 1 case, meaning I have the marginals, let's say m0 plus, m0 minus in the same notation as Enrico, that are converging to some measure in the limit. What can I say about, for example, the optimizer of the Waston 1 distance in this setting? Okay? And what we can do is the following. So in order to describe the limit behavior, I need to tell you how I can embed this problem in the continuous level. Because I have a discrete problem, which is rescaled, and I have a continuous problem. So I need to embed the continuous setting in the discrete setting into the continuous setting to talk about convergence. Because we live in two different worlds. I'm claiming that this problem will converge to some continuous problem. I need to find the right embedding from discrete to continuous to state what do I mean with the convergence result. Okay, and the embedding of the flux is meaning I have a flux on my graph, and I want to define a flux at a continuous level. And a natural way to do is the following. I'm going to look at the measure, which is essentially a one rectifiable measure, which is concentrated on the lines. And on each of the lines, I'm simply attaching the value of my j, times the direction of that vector. Okay? And the reason why this, aside the actual formula, is a natural embedding is that if I look at the constraint that I have, this is actually preserved at the continuous level. So if I embed the flux, and this flux has a discrete divergence, and the embedded flux will have the continuous divergence, which is exactly concentrated on the vertices. Okay? And then at the level of the energy, well, I already told you how we actually rescale. If I want to study constraint minimization problem, the natural thing to do will be to define a constraint functional. Okay, so a functional will take a measure and gives me exactly the discrete energy if my measure is discrete with the right divergence and plus infinity otherwise. So that the minimizer of this energy will describe exactly the minimizer of this mean flow problem I described at the beginning. Okay, and the question is, what happens when epsilon goes to 0? As I said, I need to assume that my net flux m epsilon, my marginals, are converging in some sense, and the natural topology to use, not surprisingly, in this linear growth setting is called the Kantorovich-Rubinstein norm, which we already seen in many different ways. Is just essentially the Waston 1 kind of norm in the space of probability measure. The difference here that I'm using mu as, you should imagine mu as the one which is mu plus minus mu minus. Yeah? So when we're used to Waston 1 distance between mu plus and mu minus, we're actually computing the norm of this difference, where the norm is by duality obtained in the following way, where I have constraints at the first order and constraint at the second order. Okay? It's not exactly the duality of Kantorovich, it's a little bit different. We're used more to the idea that here we don't have this constraint. We just put phi equal to 0, phi 0 equal to 0, because I have mass 0 here. And this would actually be Waston 1. Here, I need this condition essentially for any measure, which actually doesn't really give rise to the same type of dual norm. It's a bit different. On compact spaces, it's really the same. This metrizes the narrow convergence on the space of probability anyway. Okay, so the result is the following. Assume that these my marginals are converging in this norm, so in some sense, a bit stronger than the narrow convergence, so we have this first moment control. Then, almost surely, our constraint functional, meaning also the minimizers of our problem, will gamma converge with respect to the vague topology, also the narrow topology, to a functional which looks exactly in the similar structure as a discrete level. So it's a constraint functional. So I have a constraint of the divergence, and now I have a functional f home which looks in the following way. Meaning, is again something that looks like, forget about A, sorry, this should be on the full space. So it's just a F home, an homogenized effective energy density, which comes and arises from the limit behavior of my graph. And this contribution is exactly what I was trying to convince you before. I don't have much time to discuss in the details. If you're interested, we can also talk about it later. The fact that we have linear growth causes the fact that my energy might have, my fluxes could be with finite energy, even if they are singular with respect to the Lebesgue measure. Something that will never happen in the case of superlinear growth. This f form is some function I'm going to describe, and this f form infinity is called recess function, and it's simply computing what is the linear growth at infinity. So if I take a function and I take the recess of j, this just means that I'm taking, let's say, the lim sup as t goes to plus infinity. I take my function in t times j, and I divide it by t. Okay, this means I'm trying to understand how linearly grows at infinity. If my function is superlinear, this will always be plus infinity, but 1j is equal to 0, which means that to have finite energy, I cannot have the singular part here. But in the linear growth case, singular parts will appear in a natural way. Okay, and another comment I wanted to say, although I will not say much about it, is that what are the properties of this function? This function is Lipschitz with linear growth, and is not convex. As I said, I did not assume any type of convexity in the problem at the beginning. And if you're used to calculus observation results, what happens is that when I don't assume convexity, I may lose lower semi-continuity. But when I take gamma limits, I should recover semi-continuity. Yeah, because gamma limits are always lower semi-continuous. And in this vector value setting, the semi-continuity is not equivalent to convexity, but is actually the condition you need to have lower semi-continuity for divergence constraint problem is much weaker, and it's called div quasi-convexity. Yeah? It's part of a large program introduced by Fonseca and Müller called A quasi-convexity, which comes from very old problem in calculus variation, where you try to minimize function of the gradient, and you recognize that when the function are not scalar valued, there's no need to be convex to actually be lower semi-continuous. What you need is a bit lower than convex. It's called quasi-convexity. This comes back from, I think, Mori long ago. In this setting, when I have the divergence constraint, I have this condition which is called div quasi-convex, which is a bit weaker than the convexity. Yeah? Okay, but I want to use actually the final 5 minutes to give an idea about something. So how do you actually prove a result of this form? I'm not gonna, so it's based, one of the main tools is called blow-up method by Fonseca and Müller, which I don't have the time to discuss in details, but I want to convey at least one message, which is that if I want to prove a global result like this, one of the techniques that works very well in this setting is the so-called localization procedure. And so we have this problem on the full space. I want to understand how to prove a gamma convergence result. What I'm gonna do, I'm gonna take my problem and I'm gonna localize it to any type of sets in a suitable way. Yeah? And by this localization procedure will allow me to actually compute and give a formula for this limit energy behavior. How do we do it at the discrete level? Well, we take the original energy that we had, and then for every set A, I'm going to add an extra weight here, which counts how much my edge actually lives in the set A. Yeah? So if my edge is outside A, this number will be 0, so I'm going to cut my energy in an additive way, in such a way that now, if I look at A equal to RD, I recover the full energy, but I can define this for every set A. At the continuous level, it's a bit easy to do, but at the discrete level is also very natural. And then what I'm going to do, I'm going to look at cell problem, meaning I want to take, for every epsilon, I want to compute an approximation of my F home. So I'm going to fix one matrix. Okay, so I want to compute F home of a given matrix. I fix one matrix and one set, and then I look at the minimal discrete energy localized on the set between a set of competitors, which I here call representatives, which are nothing but the set of all the fluxes which are divergent 0 on the full space and have Dirichlet boundary condition in a suitable sense equal to psi on the boundary of A. And I wanted to comment here by saying that, of course, at the continuous level, this is much easier because we have a clear idea what does it mean to have Dirichlet boundary condition. Now we have a very large random graph, which we don't know very much how does it look like. So we really need to find a suitable way to describe boundary condition where we don't really have a natural way to talk about boundary at the discrete level. So this one actually depends on a suitable discretization of what is a constant flux at the continuous level that we need to define on a discrete graph. And so on the continuous level, I have, if I fix one direction, one matrix, I have the constant density measure Now, I would like to have this notion at the discrete level on a generic graph. And the question is, how do I actually discretize the constant flux on a graph? And I will conclude my talk by essentially showing an idea about how to do this. Once I have the set of representative, the limit formula will be obtained by taking the limits of the cell formulas. That is a typical thing in homogenization. I take my graph, I minimize my energy, discrete energy on a cube, on an large cube, then I rescale it and I pass to the limit. And this will actually give rise exactly to a form, and this is exactly where the stationarity comes into play. The existence of this limit is ensured almost surely by means of ergodic theorems. Okay? So I'm going to use my last minute to just show you this picture, which is the following. So what I said, I would like to share with you the fact that one of the non-trivial constructions that we really have to work hard in this paper is the following. Say that I have a given matrix in our N, which is associated with a constant density on the continuous level. How can I define a natural discretization of this on the graph? If my graph is the classical grid, that's very simple. If I have a flux, I will define that on the edges which are going up, I give one component. In the edge that go right, I give the other component, and this works just fine. But if the graph is very complicated, it's a bit unclear how to discretize the constant flux measures. So what we actually show is that there exists a linear operator that for which matrix fixed gives me a vector field on the graph, which is divergence 0, like a constant flux should be, and it behaves like the Lebesgue measure, meaning that it controls the total variation, not only the directions, but also in total variation is controlled by the Lebesgue measure. And when epsilon goes to 0, if I embed this flux, I will converge to the constant one. And the construction of this somehow constant density on the discrete level is quite involved because we have a very general graph. And it's one of the somehow toughest parts also of the paper. Okay, this was, I already mentioned, there's an application we have, of course, the convergence of the Vasten 1, meaning that if I take homogeneous energy and I rescale, this will converge almost surely to a Vasten 1 distance at the continuous level, where now the distance is not the Euclidean one, but is homogenized by taking care of the cell formula that we have. The goal, of course, is to go beyond the linear growth case, which should be simpler concerning the singularities, but on the other hand, the tools that we developed until now, they are not available for the quadratic case, for example. And with this, I conclude. Thank you very much.
So, other questions, comments? Okay, yeah, Guido.
Yeah, thanks. Thanks very much. I still don't understand this issue of the diff quasi-convexity, how it's enforced, because I'm more familiar with the usual curl quasi-convexity, where the variations have to have curl 0, i.e. there are gradients. And then in this inequality there you have in the bottom is important that the psi, so the perturbation satisfies some boundary conditions. So for example, it could be periodic, it could be Dirichlet. In the curl case doesn't make any difference. But if you don't have boundary conditions, then you kind of get back convexity.
Right. No, by the way, yeah, I should have written CC on the cube here. There was a typo.
Ah, it's a CC.
Absolutely.
Okay, then I understand.
Yeah.
Thanks.
Sorry, didn't see that. Absolutely. Thank you. Yeah. So you already answered the question. Absolutely. No, this is a boundary condition here anyway. Yeah. And this, of course, is just a replacement of the curve condition, but with the divergence. Yes.
Hi, Lorenzo. So thanks for the talk. Do you have any cases where you can compute the effective energy? Or if I give you a specific, I mean, I guess on some specific graphs, or can you say something beyond it exists?
Well, the point is that in the periodic setting is much easier to compute. Yeah, so that's what we already discussed about is, of course, if the setting is not stationary, but actually periodic, then it's computable in the sense that you can compute it via finite dimensional minimization problem, and on specific graph, you can compute it also explicitly. In the setting where the graph is really random, and in that case, it's really hard to have an explicit computation. What you can do is you can give characterization of this. So in the case of a homogeneous function, you can describe, for example, that is induced by a norm. You can really compute the fact that it has a norm with certain properties, but the actual computation of the norm in the general setting of a stationary graph is really not available. And this has always been an issue already aside the div constraint problem in calculus of variation. And when I only have information about the law, the specific computation is actually not available. What you can do typically is bound it from below and above by comparable results, but the actual computation beyond the periodic case, as far as I know, is typically unavailable. Yeah.
Okay, I don't see any other questions, so let's thank
you.
Lorenzo again. Okay, so welcome back, and it's a pleasure to introduce Karol Botowski from Paris and also Warsaw. He will talk about optimal stochastic dominance through the lens of optimal transport. Thank you.
Thank you for the introduction. Can you hear me well? I'm going to talk about two works virtually, one with Guy Bouchiter, which is done, and the other one, it is a work in progress in collaboration with Guillaume Carlier, Quentin Merigot, and Filippo Sant'Ambrogio. So by optimal stochastic dominance, I mean a family of optimization problems when we have constraints in the form of stochastic order between probability distributions, or in this case, random variables. Now, this appears in stochastic finance, and there are many stochastic orders to choose from, but I want to concentrate on the convex order, because for convex order, we managed to find something that fits the optimal transport in some specific way. So for two probabilities, we say that they are in convex order, so nu dominates mu. If the integral of the bigger one is bigger for every convex function. So immediate implication is that the barycenters must match. The variance of the bigger measure is bigger. More generally, the covariance matrix will be bigger in the sense of induced quadratic forms. So bigger measure in the sense of convex order means for sure more spread. But its precise characterization is given by Strassen theorem. It says that the measures are ordered because this is a partial order. Measures are ordered if and only if we can find a martingale from the smaller measure to the larger one. So I'm ready to pose the problem that I want to depart from. So let's take two measures sharing the barycenter, but preferably not ordered. And we are looking for the third probability that, and they are all on RD, sorry. We are looking for third probability that dominates both in the sense of convex order. And at the same time, we want to minimize a linear total cost, where the cost function is non-negative, real valued and finite valued, and convex, automatically continuous. A typical choice will be to minimize the pth moment of the measure rho, where p is 2, which will be the most important case for us, is virtually minimizing variance. So this is a simple problem that does not, I don't think it appeared in this context of stochastic finance. And let's take a look at its dual, where we have two convex potentials that are Lagrange multipliers for the two constraints. We are maximizing the familiar functional, and the constraint says that the sum of the function cannot exceed f. Now, it resembles what we see in the classical dual Kantorovich optimal transport, but it's not quite, because there we check the condition for pairs of points. Here is just for one point, so it's really a simple addition of functions. And also here, the functions are defined on the whole space, whole RD, not only just on the supports of measures. So there's no duality gap, and if the total cost for mu and nu is finite, then we are also finite. The minimizer exists if function f is superlinear, so we can't actually take p equal 1. There are some troubles. In general, there are no uniqueness. There's no uniqueness. And yeah. Exactly. Perfect timing. Yeah, so exactly. Then it is trivial. For nu, we take rho. Thank you. That's fine. So let us take a look at two problems that we solved analytically. So First, we minimize variance, and we have two-centered Gaussians, and the solution is also a Gaussian, and the covariance matrix is a max of the two covariance matrices. In what sense? In the sense that R must be bigger than both M and N, in the sense of induced quadratic forms, and it has to have the smallest trace, because trace of R is variance of rho. And for Gaussians, convex order is characterized exactly by order between matrices. So this is the explanation behind it. And it's well defined. It has a unique formula, even two equivalent formulas, but let me not get into details. So the other example is two pairs of pair of 2-point measures. If they spaced symmetrically at the corners of a square, then the solution is four direct deltas of the same mass, also at vertices of a square. If the position is more generic, then we also have a 4-point solution, but also at corners of a rectangle. But the orientation of this rectangle is non-trivial. We found a formula for it. So that's that. And also, let's take a look at some numerical simulations. So we have mu is now Lebesgue measure on a unit square, so restricted to a unit square, and u is 5 direct deltas. So let's discretize mu and apply some numerical method that I will mention later. And for p equal 2, so we minimize variance, it looks like this. So it's quite geometric. We may expect that in those 5 regions, we have Lebesgue measure. Around it, partially, we have one-dimensional Hausdorff measure. And at the vertices, we have also direct deltas, direct delta masses. So let's take a look what happens if we decrease p. So we see some curves appearing, and with p going to 1, when the numerical method collapses, this mass seems to collapse, in this different sense as well, in the center. Going the other way, for p equal 3, also we have some curves appearing, but the shapes are actually different. Now I want to say a few things about why we ended up studying this problem. So I want to start from so-called Zolotarev distance, which I believe is not so popular. So for each natural k, we define it as, we're looking for a smooth function u which maximizes the integral respect to the difference of the measures. And we are bounding point by point the operator norm of the k derivative, or equivalently, we are bounding the Lipschitz constant of the k minus y1 derivative. So for k equal 1, we have what we've seen already twice today. We bound the Lipschitz constant of the function itself. For k equal 2, we bound the Lipschitz constant of the gradient. Now, in a short paper by Belili and Heinisch, they proved that the Zolotarev distance is actually equivalent to the WK Wasserstein distance in the sense of the induced topology. So convergence, we have convergence if and only if we have weak convergence of measures and convergence of kth moments. Now, this is not shocking for k equal 1 because we have something that we've seen in the talk of Enrico and then also Lorenzo today. So we have Rubinstein-Kantorowicz duality, which says that those metrics are exactly the same for k equal 1. So what we did with Guy Bouchiter, we like to see it as a second-order counterpart of that. If we take the total cost in this optimal dominance problem for k, for the cost, quadratic cost specifically, then after subtracting the mean of the variances, we recover the Zolotarev, second-order Zolotarev distance. So the thing that we have here. Yeah, okay. So I want to. No. Sorry, which theorem? No. Yes. So let me say a few words about the proof. I will just sketch it. So by J, I will denote this energy, this total cost in the optimal dominance problem. Actually, I will use the dual formulation to prove it. First observation is that this constraint can be rewritten as this one. So we bound the Hessian between minus identity and identity. And this way, we have a connection to convexity, because this is equivalent to the pair of functions 1/2 norm squared plus and minus u being convex. And once we have that, one inequality is very, very quick. I'll skip the details. And the other one is more difficult. And to achieve it, I will make a comment. I will introduce something that may be seen as a counterpart of the C transform in classical optimal transport. So we take an admissible pair, it satisfies the constraint, so I rewrite this constraint as this. This is for any f, not only for quadratic function, for any convex cost. Now, since psi is convex, it also satisfies this, so we can take convex envelope on the right-hand side. It is actually a great candidate for improving psi. So for psi, I will take this convex envelope. I would denote it as a diamond transform. So this way, the pair is still admissible, and we will not decrease the value of psi pointwisely. So I managed to improve the pair, and I can reiterate, use the double diamond transform, etc., etc. So now the key lemma is for the quadratic cost exactly. This was for any convex cost. But for quadratic cost, we can prove that this difference is convex already. Why is it important? Because this is the formula. I'm not sure if you can see it. It's very important. Can you see it? Okay, sure. Mm-hmm. So once we have this, which I hope you do see it, then it means that we just can skip the convex envelope, and you have this equality, which can be seen as a counterpart for what we have. If this for optimal transform, if distance is a cost, then the second C transform is minus the first C transform. So this is very similar in spirit, and the rest of the proof is also very similar in spirit to proving Rubinstein duality, Rubinstein-Kantorovich duality, that Z1 is equal W1. So I will not get into the details. These are the main components. So now on to the real reason why we started the study. So I'm a civil engineer by education, and in my PhD thesis I studied optimal design of engineering structures, and grillage is a type of such a structure. It's a system of beams that constitute the structure of the ceiling. Now the question is whether we should stick to those conventional designs, or maybe we should do something bolder to save the material, save the amount of the material, while maintaining the same property like rigidity, strength, and so on. This is basically the idea behind optimal design of structures. So how does it connect to these Zolotarev to distance? I rewrite this constraint again. G is the spectral norm. And now this is perfect form to dualize. When I dualize, I'm looking for sigma that is not vector valued as a Beckman problem, which I believe also in some variant appeared today, but it is matrix valued. And this is the constraint, actually. So it is a divergence of a matrix measure, which gives you a scalar distribution, and we fix it as the difference of the two measures. And we are minimizing a convex integral functional where G0 is the dual norm. In this case, it is the sum of the absolute values of the eigenvalues. And this is exactly the optimal grillage problem. Sigma, as it is matrix valued, it has an interpretation of a tensor in the plate of the ceiling. And once sigma is concentrated on a graph, it has an interpretation of a grillage that we see here. This is an equilibrium equation of such a grillage. How do we interpret data? So we can see it as the top view, and we look at the ceiling. So gray is a concrete slab. Mu represents its weight. This weight is to be transferred through the grillage to the 5 columns, to the upwards reactions in the 5 columns. Now, this is the numerical simulation of such a grillage after discretization of mu. So what we are seeing here is a sigma that is concentrated on a graph, essentially. It is rank 1 with like the direction is aligned with the direction of those beams, and such a measure has a sign, and the colors are to distinguish between plus and minus. Now, already 7 years ago, I looked at the many analytical solutions available in the literature. This problem has been studied since the 70s. And it was baffling for me. How is it possible that the trajectories of those sigma are piecewise straight? Because in optimal design for engineers, it's typical to have curves, to use curves. And I was thinking whether there is like some optimal transport explanation behind that. This is how my collaboration with Guy Bouchiter started. And here we are. Then there was this connection to this dominance problem. So how do I actually use this equality to show some structure behind the solution sigma? So now Z2 is equal to this minimal energy in the grillage problem. J is, we are back to the primal formulation for the optimal dominance problem. And let's say I have the solution rho, this optimal dominant. Then I take any martingale between mu and rho, and such a martingale exists by Strassen theorem. Any martingale, there's no optimality involved. And I do the same from mu to rho. And then I construct two positive semi-definite matrix measures by essentially integrating 1D measure on segments that is rank 1 and has a linearly varying density. So on an example, I look for a measure rho. I build a martingale between mu and rho. And with this formula, I build sigma plus. I do the same between mu and rho. Eventually, I subtract the two, and I get the solution of the optimal grillage problem. Sorry, depend on? Yeah.
So in principle, gamma plus and gamma minus are very non-unique.
Very non-unique. No. A rho is very non-unique. Those martingales are even more unique. Yeah. Sorry, more non-unique, of course. Thank you. And the sigmas will be non-unique level 2 that I form in this way. But this problem has even more uniqueness. So level 3. It has solutions that cannot be represented like this with this construction. No, more uniqueness than the other two. Yeah, more non-uniqueness. I'm sorry. Yeah, sorry, less uniqueness. I'm sorry. Sorry for that. Yeah. But yeah, the thing is that computationally finding rho is difficult because essentially we have to find a way for numerical implementation of convex constraints or for functions. And there's a large literature on that. We tried a few things, then they worked, but they didn't quite use the structure of the specific problem. And also finding those martingales, it's also a job that you have to do in post-processing if you want to find a grillage. So this conveniently takes me to a problem that we were working together with Quentin, with Filippo, and with Guillaume, that I for now call optimal transport with moments. So the thing is that I will rewrite this dual formulation of the optimal dominance problem. I will add some assumptions. Now the data is compactly supported. F is not only superlinear, but strictly convex, and also it's C1 alpha. Then I immediately get solutions of this problem, which are also C1 alpha. And I want to convince you that I can rewrite this problem in the following way. So now, instead of just looking for scalar functions, I also look for vectorial functions. Their support is, they are defined only on the support of the data, and there's no convexity constraints now. And now, instead of putting phi of z here, I put something that I would like to call a subtangential approximation starting from x, where x is arbitrary, and similar here, starting from arbitrary y. So I have an inequality for every triple of points. So the passage is quite simple, and I don't want to spend too much time on it. Once we have admissible pair here, I take the vectorial functions as the gradients. Once I have the quadruple that is admissible here, I can construct some convex functions that will give me a bigger value of the functional. So that's quite easy. But now the specific part about this is that z doesn't enter as an argument of a non-known function here. So I can play with it. Let me move all the elements that have z to the right-hand side. And now instead of testing with z, I take a least favorable scenario here with respect to z. And I can see that up to a sign, I have a convex conjugate of f here evaluated at the sum that we see here. And this where z is unique and it's of this form, which is important for later. I hope I will get to it. So we have this formulation now, and this constraint is non-linear with respect to those vector variables, but it's still convex. We can dualize it, and this is how we arrive at this optimal transport with moments, let's say. So in the dual problem, we will have the usual plan with the usual marginals, but also we will have a plan that is vector valued. And its marginals will be, let's say, moments, but not like integrated, moments of mu and nu. And what we are minimizing is that it is nonlinear, because that was nonlinear. So rather than Nicotin derivative enters f. This is not maybe very intuitive. So how do I recast optimal rho having a solution of this? So I define function zeta as this derivative, and I push forward gamma for the zeta, which makes sense because zeta takes 2 points, and it spits out the third point that is a 1 point. So on an example, I find gamma in particular, which is non-trivial even for that simple problem to find. And for every pair of points, instead of going directly, I take a detour and stop at zeta of x, y, and I leave the mass that I'm transporting there. I leave this trace. And I do that for every pair of functions, pair of points, sorry, and this way I recast the optimal row. As a byproduct, I get the martingales that I needed to construct optimal grillage. So optimal grillage here is for free. Also from the optimality conditions, if I have the quadruple that solves the dual problem, then I have an alternative formula for zeta, which will be, I don't know if you can see it, which will be important later. So even though this is not optimal transport, we found a formulation, we found a way to come up with a synchron algorithm to solve it. So I regularized the problem with the relative entropy, but only of gamma. Maybe it seems like too little, but it does the job because the dual is exactly what we want. Under the exponent, we have the expression which is supposed to be non-positive for the hard version of the constraint. So this is what we want. So in the classical optimal transport that is regularized, solving the dual, if I have a solution of the dual, I have explicit solution formulas for the solution of the primal, a unique one. And here it is no different. And the beginning is very similar to what we have in a classical OT, regularized. But then I have to get Q. I have to have the zeta, and the zeta is, I use this formula that we've seen in the previous slide. I hope you saw it. But anyway, yeah, it's explicit. So to prove that it's actually admissible, we take a look at the optimality conditions for this problem. So I build the functional, I denote the functional, and I take a look at its gradients. And if the gradient is 0, then with respect to scalar variables, then immediately I have those marginal constraints on the marginals. If I take the gradient with respect to the vector variables, it's a bit more difficult, but I hope you can believe me that after plugging this in and having the information that those gradients are 0 because it's optimal, then it will give me those conditions. So eventually we are admissible, and if we check the energy, it's the right one. So this solution is the unique. This is the unique solution of the regularized OTM problem. So how do I build the synchron update? So how do I update the first pair of variables? So in the classical formulation, I only have to update the scalar variable, and I use it with a C transform, the regularized version, and it's explicit. and it's perfect for parallel computing. It stands behind the success of the synchrone algorithm. Here it's similar, but yet different. So this is a function of this argument, of vector argument. So this function goes from RD to R. And now I take a convex conjugate of it. And this is my transform. This is how I update the scalar function. And the vectorial function is just its gradient. And I proceed symmetrically to update the size. And if I enhance the regularity of f to C11, then the solution will, the updated functions will also be C11, with the Lipschitz constant of the gradient also inherited. And it's the gradients with respect to updated functions will be 0, and similarly here, which gives me an alternate minimization scheme. So little intuition behind the transform. So let's pretend that the vectorial functions are fixed, and then I identify it as the cost function and see it as the regularized version of the optimal transport problem, the classical one. And then I know how to update the scalar, for instance, variables, for instance, phi, using this regularized transform. But then I remember the form of the C. It's this, and I see that this value doesn't depend on y, and I integrate with respect to y, so it pops up in front. And now I remember that I can play with the variable capital phi, and I should choose it, so this value, so the whole expression is maximal possible. And it's the only, at x, only the value at x matters, so I can do it independently at each point. So I replace it with a parameter, and I know that that my update is the max with respect to this parameter. And the vectorial one is the very maximizer. Now, why this is equivalent to taking this transform? Because here in this expression, x is only here. This is important. So taking a max with respect to v is exactly taking this convex conjugate. And if we think about it for a moment, the vectorial function must be the gradient in order to be the maximizer here. We have linear convergence of the algorithm. I'll skip that. We can prove it. And now just a simulation for epsilon, quite small already. This is the solution of rho and of the optimal grillage. I decrease epsilon and I converge, hopefully because we didn't prove it yet, to the analytical solution. So I redid my best to have the preprint today, but apparently Archive has a day off on Sundays. So I kindly invite you to have a look at it tomorrow. Thank you very much.
Can we go back to the formulation of the optimal grillage problem where we were discussing the extent of uniqueness and non-uniqueness?
I can go back, but it's going to take a while.
Okay. So, I mean, my question was that it looked like, unless is it here? No.
No, it's like 100 slides.
But somehow it still looked like minimize a convex function on a convex set. So at least the set of solutions should form a convex set, no?
Sorry, set of solutions.
The set of sigmas that attain the minimum in the optimal grillage problem.
Okay, yeah, sure.
It's the optimal grillage problem is minimizing a convex function on a convex set. So the set of solutions at least is convex.
Yes.
Okay, thanks. And so usually, I mean, I don't know, in the variants of these infinite dimensional convex problems that I've come across, usually for generic data, the convex set collapses to a point. So most data give you a point, and I don't know, maybe that doesn't happen here.
It doesn't happen. In fact, even for this problem, so this is the, I didn't check, but I believe that this is the only solution that it can construct in this way. So I think that rho is unique here, and the martingales are unique here, and so on. But in fact, even for this pair, you can show that there are solutions which are at least has a part that is absolutely continuous with respect to the Lebesgue measure that covers for the whole rectangle. It's a very, very non-unique. Thank you for the question.
Hi, really nice presentation. Is this
You're
grillage problem kind of a limit of the shape optimization problem when you reduce the, like having just Dirichlet point on the column and the weight, a constant weight on top, and you kind of shrink the height? There are some connection between the two problems?
Do you perhaps refer to Mitchell problem? Because do you know the Mitchell problem?
No, like the 3D shape optimization problem where you consider linear elasticity with the two Lamé constant, and you just, as in the problem you show, consider Dirichlet points and just a uniform mass on top of that, or a uniform load on top of that.
So I'm not sure that this answer will be exactly an answer to your question, but there is another formulation that isn't a grillage, isn't a ceiling, but it's a wall actually. So it's a different type of structure. And you can show that if you formulate a optimal shape problem, and you go with the mass that is available to distribute to 0, then this problem gamma converges to something that we called Mitchell problem, and it is very similar. This is the same, this is the same, but here we have the first divergence equal to some vector valued measure. And it is famous that this Mitchell problem, which comes from engineering and can be seen as a forming like truss structures, so consisting of bars that, for instance, we see those truss structures in bridges. And the engineers at Mitchell at the beginning of the 20th century realized that if you're trying to optimize a truss, then the limit, then in the end, you need something more than a truss, something more continuous. And this way, this Mitchell problem was born. And then people realized that you can do this asymptotic analysis. And here, if you do something similar for a plate, then people show that you do not get this result. So in another way, starting from something that is built from beams, from 1D elements, isn't what you get if you start from a continuous plate and go with the volume of the material to 0. I'm not sure if this is the same as going with the thickness to 0. There has to be some rescaling done. I'm not sure, but
anyway, thanks.
More questions, comments? Okay, so if not, let's thank again, and we have a short break. Okay, so the last speaker this morning today will be Giulia Cavagnari from the Politecnico in Milano. She will talk about dissipative and totally dissipative evolutions in Wasserstein spaces.
Okay, thank you, Luigi. Thank you to all the organizers for the very nice invitation to have a talk here. So I will present a work in collaboration with Giuseppe Savaret and Giacomo Sodini, dealing about dissipative evolutions of probability measures. Okay, so let me start by introducing the subject dealing about dissipative evolutions in Hilbert spaces, since this is the key point to understand how to deal with the problem in our measure theoretic setting of the Wasserstein space. So assume that now our framework is an Hilbert space H, calligraphic H, and it's given an operator B from H to itself, prescribing the velocity field available at points of my space, of my Hilbert space. Assume that we want to deal with well-posedness of the ordinary differential equation coming from driven by our operator B. The Cauchy problem with it. What I'm saying is true even if B is set valued, so possibly multivalued. So instead of the equation, we may have an inclusion here. So if we want to have existence as uniqueness, we can ask the operator B to be dissipative in order to have the stability contraction property of the solution of the ordinary differential inclusion. What I mean by dissipative, I mean that the scalar product between V, that is the value of the operator at X, or a selection of it, and the value of the operator at Y, scalar product with X minus Y, is negative. We can also relax this condition to be less or equal than some constant lambda times the square distance between X and Y. So dissipativity is equivalent, dissipativity of B is equivalent to the stability contraction property. Moreover, if we want to implement an implicit Euler scheme in order to get the well-posedness result, we ask B to be maximal dissipative, maximal in the sense of graph inclusion with respect to dissipative operators. It's important to mention that every dissipative operator admits a maximal dissipative extension, and a class of operators that are maximal dissipative are those that are continuous dissipative. Okay, so in the classical case, it is well known that if we can construct an implicit Euler scheme, but also an explicit one under other conditions. Yes? Continuous, if we have the multivalued case, continuous in the sense of the graph, yes. Okay, so assuming that M is maximal dissipative, we can implement an implicit Euler scheme, and we have convergence of the scheme, uniform convergence to a limit curve that is Lipschitz continuous, and also it's the unique solution of the ordinary differential inclusion. And characterized by contractive Sevi group. Moreover, we can also, Bagnilan proved that it's also possible to characterize this limit, that is the unique solution of the ordinary differential inclusion, as the unique solution of an evolution variation inequality that involves the square distance between the solution type T and a reference element of my space Y, and the scalar product on the right hand side here. Okay, so our aim and the solvability of the implicit scheme is equivalent to the maximality of B, but we can also actually think to implement an explicit Euler scheme to get well-posedness result. In this case, instead of asking maximality of the operator, we ask some local boundedness condition on the operator in order to force the scheme to remain in the domain of the operator at each step and to have convergence. So this is the classical theory of dissipative evolutions in Hilbert spaces. Our aim is to transfer this machinery to the space of probability measures. That, of course, is not an Hilbert space. So we will see which problems should we face. So from now on, this is the outline of the talk. I will present the problem in the two-Wasserstein space. And in particular, we have to face what does dissipativity means in this context. We will see an intrinsic approach to define dissipativity and allowing us to implement an explicit Euler scheme. And then we will see how we will discuss what to do with the implicit Euler scheme. Finally, we will see an example comparing the two approaches. Okay, so our context is the following. We want to study the problem of generation of contractive semigroups driven by probability vector fields. So now my ordinary differential inclusion is replaced by a measure differential inclusion, whose meaning we have to understand what it is, where the evolving state is a measure, probability measure with finite second moment, and the role of the operator B of before is now replaced by an operator that is called the probability vector field, because when evaluated at the state of the system, that is a measure, gives me as well a measure, a probability measure, but on the space of velocities, on the tangent space actually, where with this notation, I mean the Cartesian product between H and itself, where the first copy of H has the role of the state and the second copy the role of the velocity. And with straight X, I will denote the projection on the state, and with straight V, the projection on the second element, that is the velocity. H for us is a separable Hilbert space. Nothing to do with the Hilbert space calligraphic H of before. It's just the space where my probability measures live. Even when H is RD, still it's interesting this study. Okay, so what is the role of the probability vector field? The role is basically the same of the Hilbertian case. At each, when evaluated at a measure, it gives me, in this case, a probability measure on the velocities. So thinking about, for instance, this picture, if my measure mu, for instance, is concentrated on 3 deltas, my probability vector field evaluated at each point in the support of mu is just a measure that represents the distribution, statistical distribution of velocities available at this point x. Sorry. Okay. So if just graphically, my probability vector field evaluated at mu is a probability measure on the tangent space h times h. So it's a measure here, was such that the projection on the first copy of h that plays the role of the state gives me the measure mu itself where my probability vector field is evaluated. And when we consider the sections, so we disintegrate the probability vector field with respect to the projection, the section here is a probability measure on the velocity space. Measures the velocities available at x. Okay. In general, as for the Hilbertian case, also my probability vector field may be multivalued. So here at x, I may have a set of probability measures on the velocities, in principle. Okay. But even the single value case is interesting. Okay. A particular case of probability vector field that actually forces this measure differential inclusion to become the continuity equation driven by a classical vector field is the case in which my probability vector field is actually deterministic. By deterministic, I mean that is concentrated on the graph of a function of a vector field f that for any point x gives me a velocity on the space h itself. It's a particular case that we call deterministic. Okay, so some examples of probability vector fields. In the examples of deterministic case, for instance, thinking about application in multi-agent systems, is the case in which my probability vector field is concentrated on the graph of a velocity f that is given by the sum of a drift and an interaction energy, for instance. Or an example that we may think about that I will recall at the end of the talk is, for instance, coming of a more stochastic taste. So consider, for instance, a vector field G that depends on the realization of some, on maybe a space of indexes. Omega may be a space of indexes, for instance. And we take the barycenter of G with respect to this, to omega, with respect to the probability that we put on omega. And with this barycentric velocity, we build our probability vector field. This is an example of deterministic probability vector field, thinking about stochastic applications, for instance, in stochastic gradient descent. Also, this very linked to this example is another interesting example of application in the non-deterministic case. So now instead of considering a probability vector field that is concentrated on the graph of the barycenter of G, we consider a probability vector field given by the image of the projection ng of the measure that is the tensor product between mu and the reference measure P of the space omega. Okay, I will discuss these two examples later on. What I mentioned is that basically this example here above, in this example, this F above is exactly the barycenter of this second example here, and will have a special properties. Another example in the non-deterministic case is the case in which my probability vector field is given at each. We have, for instance, think about confinement problems. We have a convex set where we want to confine our dynamics. At each point in the boundary, my probability vector field has measures that points inside my set. Okay. So the question is, so these were some examples. Now the question is, in the Hilbertian case, the dissipativity condition was the key ingredient in order to have well-posedness results, in order to implement, to have a convergence of the schemes. Now the problem is that in the space, the Wasserstein space is not, even a vector space is not an Hilbert space. So how can we define a suitable notion of dissipativity now that we don't have a scalar product available? Okay. The key idea is that even in the Hilbertian setting, the dissipativity condition can be seen as actually a condition on the metric. Indeed, we can write the scalar product involved in the definition of dissipativity as the derivative at 0 of the square distance between the first order expansion starting from x with direction v of some tau units, and the same starting from y with direction w, where v is the value of the operator at x and w the value of the operator at y. So we are taking 2 points x and y. We are taking the first order expansion given by my operator at x and at y. We are considering the square distance between the two expansions, and we are considering the derivative at tau equal to 0. This coincides with the scalar product involved in the definition of dissipativity, and so asking the dissipativity condition means to ask that this square distance is decreasing. And so basically, the dissipativity of the operator implies that the operator involved in the explicit Euler scheme is an infinitesimal contraction. Moreover, what is important, since this square distance with respect to tau is convex, we can also have the same property backwards. And so we have that the resolvent operator, that is the one associated, that is used in the implicit Euler scheme, is a contraction. And so we have also the contraction property of the implicit Euler scheme, and so can be solved. Okay, so the idea is that we can use this. So since dissipativity can be written in terms of the square distance, let's use this fact now in the Wasserstein case, where we have the notion of Wasserstein distance. We just have to replace the role of this x tau and y tau in a suitable way. So what is the role of x tau? The role of x tau is basically the first order expansion. Now I call mu my x. Okay, mu is now the state. F of mu is the value of the operator at mu. And the first order expansion of mu in the direction given by the field is exactly given by the push forward of the exponential map via my probability vector field available at mu. I do the same starting from nu. and I compute the square vast distance between the two and the right derivative when at t equal to 0, at tau equal to 0. I define our pseudo-scalar product between the two priority vector fields to be this derivative of t square distance here. And we can prove that this right derivative coincides with the minimum of the standard Hilbertian scalar product of the probabilistic of the random variable representing my priority vector field at mu and nu. Among the where the minimum is taken among the class of all the tetra pairs of random variables representing mu and nu, in such a way that along the base xy we have an optimal plan. The law of the joint law is an optimal plan. Okay. I just mentioned that if we take the left derivative, instead of a minimum, we have the maximum. So the left derivative is greater than the right. Okay. So now we have we choose to give this notion of dissipativity following this metric approach, this intrinsic approach, and so we say that my priority vector field is metrically dissipative whenever the scalar product defined in this way is less or equal than 0. Now the question is, does this condition ensure to have convergence of the explicit scheme and of the implicit scheme? And then can we characterize the limit as in the classical Hilbertian case as by some evolution variation inequality in our vast system framework? Okay, concerning the explicit Euler schema, basically there is no problem. Okay, we can implement an explicit Euler schema even in this measure theoretic framework in the standard way. So we define the time step, the following measure at the time step n+1 as the first order expansion starting from the previous one given by the value of f there. We take the affine interpolants between the measures of the scheme. And we notice that the vastness and distance between two subsequent elements of the scheme is actually controlled by the variance of the probability vector field at the step n. So basically, if we ask some boundedness condition on the variance of the probability vector field, we have a convergence of our explicit scheme. This is what indeed we ask. So we are able to prove that under this condition of local boundedness of the operator, we have a convergence of the explicit Euler scheme uniformly to a limit curve that is Lipschitz continuous. And also we are able to prove that this limit curve is the unique solution, evolution variation inequality solution for my probability vector field f. I didn't wrote now what does it mean evolution variation inequality here because it's the same of the Hilbertian case where you replace the scalar product with the pseudo scalar product here. Yes. The dissipativity is enough. Yes. Also in the classical case, it's like yeah, no. Yeah, dissipativity is enough. Dissipativity and local boundedness. Yes. Okay. So the problem actually arises when we want to implement the implicit Euler scheme. Indeed, I mentioned, dealing with the Hilbertian case, that the contraction property of the resolvent operator follows by two ingredients: the dissipativity of the operator that now we have if we ask this metric dissipativity condition, and the convexity of the square distance with respect to tau of the first order expansion. The problem is that in the vast system case, the square distance between the square of access and distance between the two expansion is not convex. Actually, it is semi-concave. So it's a problem to have some contraction of the resolvent. Actually, it's not the only problem, but for sure it's it's a problem. So how to deal with the implicit Euler scheme now? Basically, we realized that the condition of metric dissipativity in some examples, actually some examples of probability vector fields, for instance, those that are deterministic and continuous, if they are dissipative, they are also more than dissipative. They satisfy a so-called total dissipativity condition. This is just consideration that in order to do this machinery that I want to present now. This was just a consideration. So how to deal with the implicit scheme? Basically, we do the following procedure. We take our problem that is set in the space of probability measures and we lift it in the space of random variables whose law are our probability measures. We fix a reference probability space sufficiently rich, so omega, Polish, B without P without atoms, sufficiently rich in order to describe our measures. And so now we pass from our metric setting to the Hilbertian setting of the space L2 with respect to P, where the random variables lives. So now mu, the role played by mu will be played by the random variable whose law is mu, and the role played by my operator probability vector field F will be played by an operator B that is such that its law is my probability vector field F. Why we do this? Because now that we lift our problem in this space L2, L2 is a Hilbert space, so we can apply the classical theory valid in Hilbert spaces. We can work with the implicit Euler scheme here, and then we hope to be able to pass back to our space of probability measures in order to deduce nice convergence of some kind of implicit Euler schema here. The question is to which property of F does the dissipativity of operator B that we have to ask in the Hilbertian case, dissipativity of B, which kind of dissipativity condition on F produces? And also the maximality that we have to ask on B in order to work with the implicit Euler scheme in the Hilbertian case. Does it transfer to some kind of maximality of my operator in the space of probabilities? So now we have to understand that is the link between B and F. So we define B as the set of all the pairs XV whose law is in F. Just naturally, we call B Lagrangian parameterization of F. It's important to notice that a Lagrangian parameterization for F is law invariant, in the sense that if we know that XV belongs to B, and we know that we have another pair YW with same law as XV, then by definition also YW should belong to B. So B is not a whatever operator in a space of two. Is a particular operator that is law invariant. Okay, it's important, of course, to notice that there is a one-to-one correspondence between F and the law invariant B. And basically, we can say that by definition, we say that F is totally dissipative. In a moment, I will describe what does it mean in practice. It's totally dissipative if its Lagrangian representation is dissipative. We will see in a moment that this totally dissipativity condition is stronger than the metric one. So basically, if this condition is true. Here I didn't, I don't have time to discuss, but the fact that the maximality of F among all the totally dissipative operators corresponds to a maximality of B among the dissipative operator in L2 is not a straightforward thing. Needs to study better also extension results for Lipschitz functions in the classical case. So, but we have a full correspondence also between maximality. So this is the relation between metric dissipativity and total dissipativity. While if we write metric dissipativity using the scalar product and writing it in terms of the random variables, metric dissipativity means that there exists a way to describe f of mu and f of mu in such a way that along the base we have optimality, such that we have the dissipativity condition. The total dissipativity means that for every realization, for every representation of mu and of f of mu and f of mu, whatever is the plan on the base, we have the property of dissipativity. So of course, total dissipativity implies the metric one. But in some cases, they coincide if my operator is nice. So we are able to prove that if my operator is maximal totally dissipative, then by this argument of lifting, we are able to prove that the implicit Euler scheme at the level also of measures is solvable. It uniformly converges to a curve that is Lipschitz. This curve, being Lipschitz, is of course a solution of some continuity equation, and is the solution of unique solution of the continuity equation driven by the element of minimal norm of my operator that turns out to be concentrated on a map. This limit is also the unique evolution variation inequality solution for my operator, and it's characterized via the semigroup associated to the problem, to the ordinary to the Cauchy problem in the lifted space. So in the lifted space, since B is maximal dissipative, we have existence and uniqueness of solution characterized by a semigroup. And this semigroup defines also the semigroup at the level of measures and characterizes my limiting solution. So there is a nice correspondence between the structure in the lifted space and the structure in the space of measures. And then we have a nice property that if the support of the initial measure is finite, then the cardinality of the support of the evolving measure will be finite and non-increasing. Okay, I don't know. How much time do I have, if I have? Maybe I don't have. Okay, thank you. So in the last, very last part, now we have seen how to implement the explicit scheme and some strategy to implement an implicit one via this lifting technique. We want to compare the two in some cases. Of course, if my operator satisfies all the conditions, nice, then the two solutions given by the explicit and the implicit coincides. But what happens in case in which my operator maybe is not totally dissipative, so I cannot apply the implicit Euler scheme to F, but its barycenter is totally dissipative. So we want to focus now on situations in which the operator has a totally dissipative barycenter. And we want to apply the explicit Euler scheme to my operator, that is just metrically dissipative, and the implicit Euler scheme on the barycenter, on the extension, maximum extension of the barycenter. So here I just define the definition of barycenter that is intuitive. What is the example that we have in mind is exactly the example of the stochastic field, in which we ask G to be dissipative for any omega. Now, this omega is not the omega of the lifting, is another one. If G is dissipative, then the operator F here is metrically dissipative, and the barycentric operator F tilde is totally dissipative, actually. So we may want to compare what happens if we study the explicit Euler scheme for F, that can be done, and the implicit Euler scheme for its barycenter that is totally dissipative. Okay, it turns out that in general, so in particular in that example, if we have an operator that is such that its barycenter is totally dissipative, then my operator is metrically dissipative. Actually, it's more than metrically dissipative. It's satisfy a better condition that here I didn't introduce. So if we assume that my operator has barycenter that is totally dissipative, in particular my operator will be metrically dissipative, I can apply the implicit Euler scheme to the barycenter, to the maximum extension of the barycenter, and explicit to the operator F. And what we get is that the measure that is obtained by using the implicit Euler scheme on a maximal totally dissipative extension of the barycenter is not only an evolution variation, the unique evolution variation inequality of the maximal extension of the barycenter, but is also an AVI solution for F. But since the AVI solution for F was unique, it coincides with the one of the explicit Euler scheme that we build on the operator F. Then here, I don't think I have time, but we also studied this comparison not only at the level of the limit mu, of the curve mu, but also at the level of the probabilistic representation of the explicit Euler scheme, so a measure eta concentrated on continuous paths, and probabilistic representation of the implicit Euler scheme for the barycenter, and we are able to prove a convergence of a probabilistic representation for the explicit scheme towards the unique probabilistic representation of the implicit scheme for the barycenter. Okay, so finally, okay, there are some pro and cons in the use of the explicit Euler scheme. That is the fact that it's a more intrinsic notion based on the metric notion. Some pro in using in adopting the lifting technique to implement the implicit scheme, because you pass to a set that is Hilbertian. Of course, we would like to reduce the assumption of total dissipativity and try to work directly on the space of measures to implement a sort of implicit Euler scheme there without passing by the lifting technique. But this is still open problem. Okay, so thank you for your attention.
So thank you very much. Questions, comments?
So dissipative operators are connected to subdifferential of convex functions, no? So what are the examples of, I don't know, convex functionals that have a totally dissipative operator as a subdifferential in the Wasserstein case?
Okay, this is a nice question. Actually, I have a slide on this. Okay. Okay, let me discuss briefly. Okay, so if you consider a functional in the space of probabilities that is continuous and geodesically convex, and you take the standard notion of the Wasserstein notion of subdifferential of it. Actually, the problem is that the opposite of the subdifferential of phi, even if phi is actually totally convex, so convex along any coupling, this opposite of the subdifferential of phi is not totally dissipative. I will write in a moment. What is important is to notice that, okay, we can, starting from phi and not from the subdifferential of phi, starting from phi, we can lift phi to an operator psi that lives in the Hilbertian space L2. And the subdifferential of psi is totally dissipative. And the element of minimal norm of the subdifferential of psi coincides with the element of minimal norm of the subdifferential of phi. And since it's the element of minimal norm, the one that counts actually in the implicit scheme, we can prove the result that I wrote here, that actually we have the we produce the unique gradient flow by the implicit scheme with the technique of the lifting technique. Yeah, but it's very. I mean, it's not obvious this thing. Yes.
Any more question, comment? Okay, so if not, let's thank Julia and all today's speakers.
Okay.